So, as I was saying, hello everybody.
Sorry, I have to introduce you. This is Dottie, and this is his talk.
Yeah. I work in the platform toolchain team at Red Hat, and so this talk is going to be about discussing with you guys about the new kinds of debug info formats that are coming that we're seeing coming in the kernel space, and tell you guys about how we're using the existing debug info infrastructure that is there already to perform some analysis of, I was told not to talk about kernel ABI, so I will talk about kernel module interface. So the idea is to show quickly what we do with the debug info today, and so that we know what would be nice to expect from the new debug info formats that are coming, so that we can keep doing what we're doing today, and even getting better better experience. So first of all, why are we interested in analysis, in looking at the kernel module interface from a binary standpoint? So this is mainly due to the fact that we're having a different perspective here. We're having the perspective of a kernel maintainer who is usually dealing with long-term support versions. And in that context, that kernel maintainer doesn't want the ABI to change in an incompatible way across updates of a given LTS, I would say, main version. So the idea is that maintainer or those maintainers want to see the changes that impact the kernel module interface, well, the interface exposed by the kernel to its modules. Want to see those changes in order to review them, to be sure he agrees. Those changes are what he intended, and also to probably alert us automatically or semi-automatically about some changes that might be not acceptable. So we look at the binaries directly as opposed to looking at source code, because by doing that, we capture not only what's carried by the source code, but also all the stuff that happens to the source code after you've written it. Like if you change, I don't know, the tool chain, that might impact the source code. So if you just look at the source code, you might miss all those things. So that's the perspective we're taking here. So without talking too much, for those who don't know, I wanted to just show you how you can be useful to maintainers in a very simple way. So I'm gonna drive you through a real world, a small example of what we are showing today. So can you read this? If you can't, I don't know what to do.
Is the size big enough for you guys at the bottom?
If it's not big enough, you can come. You could. Okay. Oh, so it's good. Yeah, but there is room, in the front where we're not eating people yet. So let's take a real example here of a tool that we have that uses the infrastructure we have today to compare two binaries, okay? These can be, I don't know, some kernel module or whatever. These are small binaries, and let's see what the changes to the interface exposed by the binary interface of this thing is. So basically, this is what the tool is gonna show you, and I've just highlighted the stuff so that we can follow it easily. So the first part is just a an abstract of the changes that were detected. So basically, we're seeing that there was one function that changed. And so what does that mean? So then it goes on saying that the function that changed, the name of the function that changed is function 0. It tells you its type and so on and so forth. And it says that the return type has changed from an integer to a char. The type size has changed from 32-bit to 8-bit. The first parameter has changed as well. It was the parameter has a type. It's a pointer type, and what's changed is the pointed to type. Okay, it got a data member inserted at a certain offset, and it gives you the source line. And it says that the second parameter was removed from the function. So this is the level of detail that we are having today from the current infrastructure. Even though we're looking just at the binary, we're referring to the source code in the reports, so that we can be useful to, well, normal people. Okay. So basically, what I'm trying to say is that we're looking at more than just ELF symbols. So obviously, we're reading the debug information. We're building we're doing compiler stuff, basically. We're building an in-memory internal representation of what I would call ABI artifacts. So basically, we're building a graph of the functions, variables, their types. That IR can be serialized to disk to save a snapshot of what the ABI is, but that is just if needed. We can also compare the IRs, because obviously we want to compare stuff, right? And the result of the comparison is not text. It's also an IR, an internal representation. That can be analyzed to decide whether the changes are worthwhile or just walking that IR to emit change reports, basically. So for the new debug info formats that are coming, I'm talking about CTF, BTF, or anything more. I don't know if there's anything more coming. People are talking about some compact dwarf thing, but anyway, it will be very. So this is where the discussion, I would say, starts. Or it will be very interesting that we could still do what we're doing. What I've showed you in the previous slides. So what do we need for that? Basically, we would need full type description for programmers levels artifact. By that I mean function, things that are meaningful to programmers. So not ELF section, details and stuff like that. Nobody cares about those things. I'm talking about functions, variables, their types, whether the type is a structure, a pointer, qualified type, things with consts, things like that. Yeah, please.
If I could jump in here and just,
of course,
just query whether you mean only those that are visible in the ELF symbol table or absolutely all of them, and whether you mean only top-level types or even types that are only defined inside functions. I can't imagine you care about the latter, but you might.
So, yeah, that's an interesting question. Yeah.
So, back when I was at Red Hat, I always took the most delight in changing the ABI whilst the stupid tools that I did. So there's a whole bunch of things you can do to screw over people that this tool will not and cannot ever find.
Of course. But that's absolutely true, right? It's some kind of a mouse and cat kind of.
No, there's a whole class of changes you can do that are fundamentally impossible to
like I'm talking about ABI kind of stuff.
No,
right?
this is ABI. So, for example, you have an object and it has an initialization function and a destruction function and some other functions to use it during the lifetime. You can change the rules. For example, some function might be optional and then make it mandatory in the API. This will never ever catch that. You can reverse the order that two functions must be called.
Yes.
This will again never ever
Sure.
find anything.
But this is
like
not
that.
the structural. This is a matter of behavior.
I know.
So it's not. Yeah. To me, to me, I mean,
Please do tell your
it's gonna be,
customer.
I mean, it's gonna be caught by other types of checking, like anything that has to do with the behavior of a program can be caught by, dynamic testing. I mean, runtime testing. So this is not this is not exclusive to runtime testing. I'm not saying that you should not do runtime testing. We should do it. But the earlier you catch things, the better. The easier it is to fix them. So these ABI thing we're doing is really to be able to catch things earlier, even before those expensive runtime stuff. So the thing you were talking about, I think, maybe I'm wrong, but I think these are not about the structure of the entry points that are exposed by the binary. It's about the behavior, like the order of initialization and stuff like that. Yeah, that has to be caught by runtime testing. So to get back to your question, the philosophy that we are using today is the more I can get, the more information I can get, the better. And then afterwards, I will filter what I don't need. So you were talking about, for instance, types that are, or even functions that are not necessarily exposed. Okay. The thing is that, so let us, it's nice to have examples. When you have a pattern that is used by everyone in coding in C, when you want to hide the private data members of a structure. So the structure will have just one data member, which is going to be a pointer to the private structure itself. And that private structure itself is going to be defined in a file, a .c file, without header file. So it is supposedly private, okay? And then the public type, the one with just one data member that is a pointer, is going to be exposed in the header file. So I guess your question will be, do we care if there is a change in the private part, for instance, of the type, the one that is not that is supposed to be private? And initially, I was thinking that no. Okay, and we had real life examples of people who were who came to me and saying, yeah, this is not an ABI change, but I still want to see the change because I didn't. It was a real world case where just changing a define, the value of a define macro was changing some stuff in the private, section, and the define macro stuff couldn't be caught because, of course, after the pre-processing stage, boom, it's gone and it's not captured in dwarf, right? And so what we did, and obviously we follow pointers during the analysis, right? So we were saying those things, but we were discarding them very early. So what we did is that, we just give ourselves the possibility to see all those things, but then discard them at the user's will. Yeah.
You have 15 minutes more, so if you want to discuss about
Yeah. So go ahead. So did I?
Later.
Yeah. So full type description of our functions. So what do I mean by that? For instance, I mean that I would like to have the return types of the functions described. For instance, that's something that you don't have in the in plain ELF, So we would like to have all the types of the parameter types. But for instance, if the parameter type is a pointer, to another type, I would like to be able to walk through that pointer and discover, that other type. So not pack it and say, oh, pointer to type foo is a new type, pointer to type foo. No, I would like to have the ability to say it's a pointer to a type foo that exists and walk through that graph. And so this kind of thing. Very important. Yeah, I see that some folks are in the know. Yeah. So deduplication of type descriptions. Yeah, compiler people, like using lingo. So I'll try to explain what that means. So basically, the way dwarf is the dwarf pipeline processing is organized today is that the compiler sees one compilation unit at a time, basically. I'm not talking about LTO kind of stuff, but link time optimization. But at compile time, the compiler supposedly sees one compilation unit at a time. And so in that compilation unit, what it does is that it will emit debug information for what it sees, okay? Including all the header files that are included and so on and so forth. That is emitted in a relocatable, okay, a .o file. And then it moves to the next file it compiles. And it does the same thing. So suppose, for instance, yeah, please go ahead.
Does it also emit structure information for structures that aren't actually used in that translation?
Yes.
Okay.
If it is declared, not necessarily defined, it's supposed to be emitted. So, and it does the same thing for the next compilation unit. So suppose that in the first one, we had an integer type, int, defined. We'll have an integer type defined in the second compilation unit as well, and in the third, in the fourth, et cetera, et cetera. So there is duplication of types definition in dwarf. And then what the linker does is that it will take all these .o files, concatenate their debug info, their dwarf stuff, because the linker doesn't go and analyze what's inside the dwarf. It just takes it and concatenate everything and sticks that in the final binary, that it is constructing. So in the end, in that final binary, you have int defined zillions of time. So it is duplicated. And you can imagine what you have for structures with pointers, that points to types and blah, 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 blah. You have like a lot of duplication. And so what we spend a lot of time at runtime in libabigail, for instance, deduplicating those types, making sure that if you have two integers, you just keep one. And if you have two types of the same name in the binary, and if they're the same, so there are two conditions there. If you have two types that have the same name, and if they're the same type, so structurally, you have to compare their structure, member-wise, then it's the same type. So you drop the second one. Okay? And we do that across all the millions of type occurrences that you have in the binary. So we spend a lot of time doing that. And so it will be extremely nice, like extremely useful, that those new debug info formats, do that at emitting time, when they emit the stuff. But this is quite challenging. So imagine, for instance, let's take an hypothetical example, something that will never happen in real life, probably, a kernel with modules. So you will have the kernel, for instance, with 3,000 something modules, each one defining its debug info, So if you want to build the representation, an in-memory representation of that, representation must be the union of the representation of VM Linux, the binary, hypothetical example, and of all the 3,000 something modules in memory. And then you deduplicate that. So I think that there is probably some pre-processing, some post-processing that should happen there. Because I think the compiler is gonna still see one compile unit at a time and probably emit one module at a time, et cetera, et cetera. But still, it will be extremely useful to have that thing done. I think that the BTF guys are talking about that in one of the blog posts I've seen from the Facebook guys talking about that. But I don't know what's the state of things with CTF.
I can specifically say that we have a new deduplicator being written for the old deduplicator with a kernel with 3,000 modules. At the moment, it takes about, well, before 3 weeks ago, it took a minute and a half to emit about 6 meg of compressed CTF describing all of them. Now it takes about 40 seconds to emit about 5.5 meg describing all of them. Without that, without deduplication, you get 55 million types and hundreds of meg of repeated junk. So you really need deduplication. And we've got it. So.
Yeah, exactly. And for instance, today, so Matthias is here. I don't know if you were to his talk yesterday, where he was presenting, their process about ABI and stuff in Android. We've been working on this just to give you, kind of time, scale. I think now on a regular laptop we're down to emit the entire ABI. So it's not just the deduplication. So you read the binaries, the thousands binaries. You do everything and you save it on disk. Deduplication included because we have to do it. So we're around 120 seconds or something, right? I mean, for the full-blown kernel, the Android guys are like faster because they do, they take corners with very high velocity or something.
So it takes longer than to actually build a kernel.
I don't know how long it takes on those machines to. 120 seconds. I think it takes more than that to build a kernel, no?
It takes, like, as a roughly measurement, 2 minutes to build, and
I have one. That's redundancy. The Android kernel builds in that configuration that I'm testing in roughly 2 minutes, and the extraction of the ABI is roughly 20 seconds, 15 seconds, depends a bit.
Yeah. So so we're using a lot of heuristics and so on and so forth to speed up that thing, and a lot of mental power, and it will be very, very useful to have that. So
I should point out that unlike Torf, with CTF we are deduplicating at linking time, and we are in the process of putting that logic in binutils itself in the linker.
So at link time, but what about all those modules? Because you don't see, So, I mean, that's super nice already for VM Linux.
They specialized, most of the type merging and deduplication stuff is in a library which binutils produces, and there is a specialized kernel-side deduplicator, which does a similar job on a kernel scale and knows what modules are and that sort of thing.
But
okay,
we will see that later in the.
Yes.
Okay, that's yeah. So I guess this is my request for you fine fellows, and if you don't have any more questions, thank you very much.
We have like 5 minutes for questions, complaints. No, not yet.
Can I just say Libavigail is awesome?
Thank you very much.
Okay, so let's process to the next one. Yeah.
Thank you.
have to speak in less. Or maybe that one. So this one is true to ask questions, and this is to answer. Yes, that's true. Is it?
There do seem to be a lot of people using the Xbox as presentation devices than Macs now.
Okay.
That's changed.
Is it all right? Yeah. Okay. So, can I be heard correctly?
Do
I will start now, I think.
Okay. Can you hear me?
Well, I can hear you, but it's not due to the mic.
Yeah. I guess.
Maybe you want 10 coffees? Just use that one.
Okay, do you hear me?
Yeah.
How do you do this?
Hey, hey, hey. I'll just. Hey, hey, hey. I'll just check. Hey, hey. It's too low. Okay. So, my name is Maciej Życki. Welcome to this presentation.
It's on. It's on. It's just too far away.
Hey, hey, hey. Hey, hey, hey. Hey, hey. Hey, 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 hey. Hey, hey. Okay. So, this one does work, apparently. Okay, great. So, my name is Maciej Życki, and this is my first presentation during my university days, which was sometime last century. So, this may be a bit harsh, hopefully not. And I came here, I'm myself and Dmitry, we're both coming to this conference and the GN Tools Codron, which is happening later this week. And we were asked by one of the GLPC maintainers, Florian Weimer, to talk about the issue of syscall wrappers in GLPC. So excuse me. I haven't been involved in that myself, although I've been contributing to GLPC and working with the community for several years now. And this will be essentially mostly a message from Florian with a request for feedback from all of you. If there's anything done better or suggestions, then these will be taken into account, and we'll carry the message to the code join in Montreal, which is happening this coming Thursday. So the motivation for having the syscalls wrapped in GLPC is there are several advantages to that. Rather than doing raw syscall calls from various applications which happen to have a need for them. There's no corresponding C library interface. So one of them is type checking, which is, I think, obvious. The other one is portability across Linux ports, which means essentially you have a C interface where you can invoke the syscall as if a usual C function, and you don't need to oh gosh. So where's this coming from?
You have a cell phone in here?
No. Yeah, so essentially, yeah. So otherwise, obviously, each of the applications which wants to use the interface would have to know all the gory details of the unique calling convention for syscalls, meaning generally writing assembly code and such stuff. Another thing is POSIX thread cancellation, which will be done.
Yeah, it's working.
Okay.
I just got interference in the mic, so sorry.
Yeah, okay. And debugging, the thing is essentially you can place a breakpoint. You can place a breakpoint or at the single entry point to at the syscall wrapper, rather than having to chase all the syscall invocations in assembly. So traditionally, all the syscalls used to be wrapped by C libraries, and GLPC used to do that as well, but a historical mistake was made at one point that we stopped doing that, and lesson has been learned, and we decided to do this again, essentially. So, but this is only going to be for the syscalls that are actually useful to applications. We're not going to expose stuff like some architectures require a syscall to set the thread pointer, for example, like x86 using an LDT entry. This is used internally by GLPC, so if it was to be exposed to an application, then all things could break, so we're not going to have that. But otherwise, there's no problem to have the syscalls. We have some guidelines prepared already. What's the syscall wrappers are supposed to look like, and why the intent is there to have them. We're not regrettably going to add them all at once. The thing is essentially there is significant effort to doing that, and each of the functions have to be documented in the GLPC manual, and that has to be reviewed. You have a question?
Is the copyright only for the documentation or also for the wrappers?
Yes, it's both for documentation and for code.
So does
obviously.
the FSF now acknowledge that there is copyright on APIs?
It's not about the API. It's about the actual piece of code. I mean,
There is no code. It's a wrapper.
It's
That
actually a piece of code.
Well, but it depends. As you say, if a little piece of code is implementing an interface and there is no creativity required for writing it, meaning that you cannot do it in a different way, lexically speaking, then use, yes, then, and in other GNU packages and programs, we have files like describing font maps, for example, which will be something similar, where we consider those files to not be copyrightable. But we will need to look at each case separately, involving lawyers probably and so on. But yeah, not everything can be copyrighted.
Yeah, and of course, you know, if the contribution is very small, there's the rule that, like, if you contribute up to like 15 lines of code, it can just go in. And if you say your proposed wrapper is going to fit into that, that's not going to be an issue. And these days, doing a copyright assignment with FSF is not that, it's usually not a big deal because this can be done electronically for many people. So
it's also not legal in a number of territories.
Well, I'm not a lawyer, so I
No,
can't speak
no,
about
me
that.
neither. I'm
But
just
I mean, you know, yes,
well.
yeah, but you know, I mean, you know, if it's void in your country, for example, that you can do this and, you know, ignore from then on. So, you know, because it's not valid anyway. So, you know, yeah, I mean, you know, that's,
But you didn't say that, right? Yeah.
yeah, no, I mean, you know, that's nothing illegal. You know, I mean, you know, if FSF requests that, you can do that, but it's not going to you know, sort of take your copyright away from you. That's you know, essentially ineffective in your for your country. So that's nothing.
You can actually do it electronically
Yes,
now?
yes. I don't know the exact details where it applies, but I believe it's for you know, private persons in the US, and I believe in Germany and a couple of other countries.
I think I did this like 2 years ago or something because I needed to get some stuff into glibc, and I think I still had to mail a letter to the US or something.
Oh.
Germany.
Well, I have done copyright assignment in Germany, from Germany, where I lived, and you can do it with the PDF.
Ah.
Yeah, so.
Okay, and the final problem with adding more wrappers is essentially we're short of reviewers. That's the usual problem. The glibc community is not very large at this time. Everyone is welcome to join us, of course, but with the task force of people that we currently have, and so many things to do, it may be quite a stretch to do this as well, especially all at the time. So if, you know, all the contributions are welcome.
Just in case people are put off by its past reputation, the glibc community is really inviting these days. It's one of the most pleasant communities I've ever contributed to.
Yeah, indeed. We are consensus-driven these days, so essentially for a change to be accepted, there has to be no serious objections for people from the community, and usually just a single acknowledgement from one of the maintainers is enough to get the change in. Okay, so here are some specific notes about our glibc project's requirements for the syscall wrappers. So we're not going to emulate syscalls that have been removed, deprecated, or are not present for whatever reason. We're just going to return NOSys, well, past the NOSys return status from the kernel. The reason for that is it's, except for very trivial cases, it has proved very error-prone and problematic. Some trivial cases are where, for example, there's a new flag added to a syscall, which, in the absence of which an older syscall can be used directly, but we'd like to avoid that. Another case is we want to have architecture-independent names of the wrappers, if at all possible. So essentially, if there's a syscall that's shared across all the architectures, we want to have it named the same across them all, because otherwise it's going to be a maintenance nightmare. A problem are also multiplexing syscalls. As I listed here, well, it's not possible to check the argument types when they are different for each of the sub-syscalls passed through the multiplexer. If there's a variable number of arguments depending on the argument types or flags or something like that, then that's also a problem. And one specific example Florian has given is the OpenAT syscall, which has gained the O_temp file flag at one point, and obviously if a wrapper didn't know this flag, it wouldn't have passed the mode argument, because it wouldn't know it's required there for this new flag as well. And some architectures have limitations in that you can't call a variadic function which has been declared with a non-variadic prototype. So we're not going to handle multiplexing syscalls, and we can make we can make exceptions for the existing examples like the futex. But in this case, this would be by using individual wrappers for the individual requests. And another point is it's preferable if a new syscall is added across all the architectures in a single kernel release, because otherwise we're going to have issues by keeping track of which syscall has been added at which release for each of the architectures. The matter of interfaces, there are some specific types that we would like to see, like ssize_t or size_t for buffer sizes. This is mainly for documentation purposes, so that we know what the interpretation of the type is, even if the kernel uses int or unsigned int. Typically, well, the silentness of the type will reflect the type of the kernel. For example, when the buffer size is an incoming type, it will be unsigned, but as a syscall return value, which can be negative in the case of an error, it will be a signed type.
Sorry, about multiplexing syscalls. Well, I just want to be careful.
Yeah.
About multiplexing syscalls, that includes something like BPF, right? For example, it's the first one that comes to my mind right now. And the idea would be to expose individual subcommands or whatever as individual wrappers. BPF map something, I don't know. Yeah.
Okay, so I just repeat that for recording. So the question was about the BPF syscall, which has a multiplex syscall, and it does exist already. So yeah, so that will be handled by having individual wrappers for all the individual requests. Yeah, so back to the types. So we want to have the long type avoided for flags, because it's not possible to determine whether the extra 32-bit, the extra high 32 bits of the flags will ever be used or not on architectures which have them. For file offsets, the pointer to off64_t is fine. However, using the type directly is problematic because of the differences in how it's passed across various architectures. Obviously, it can be in a single register or a pair of registers, and it's even more complex for as return value from a syscall. So yeah, errors have to be passed via errno and a special return value, and we make an exception for the pthread calls. And it would be very good if for each newly added syscall, all the associated types and constants were wrapped into a separate Linux UI API header, because this way we can have support in glibc for all the types and constants defined there by just using the headers from a kernel that's new enough to include that. We don't have to make any changes to the headers that we already have.
Just checking, presumably the important thing there is that it doesn't contain unrelated stuff and it doesn't contain function prototypes, because they clash. Yeah, just checking.
Okay, yeah. Okay, so that's the message essentially. Any questions or? Okay.
Okay.
Okay, I guess that's a no.
So then the syscall wrapping is clear and there is no problem with it.
Yeah.
Well, so then it changed. It totally changed from the last Plumbers in Vancouver in November, because I was there and I remember that there was a huge problem with glibc, and you guys were going to I don't know, something very drastic because you could not live with it any longer. So I am very glad to see that.
I mean, but already when it came up on the mailing list, I mean, everybody pretty quickly agreed that yes, please.
Okay, so then who has the ball on their, well, I don't know, that is a literal translation of the Spanish saying. So, who should do what now? So, because if in the libc side they are waiting, and in the kernel side you are waiting,
I think new syscalls are trickling in on the glibc side. It's not fast, but it's happening.
okay, fine. So, my question is the current situation actually moving to some resolution or not?
I'm happy to hear that wrappers are accepted or acceptable again, because this used to not be the case.
Okay.
It might help if somebody would invest in enumerating which system calls are missing.
Florian has done some of that. I've
Okay.
seen. He seems to be on top of it.
I suspect the perf one is missing.
That's a classic example of a horrifying multiplex system.
It would be. So yeah.
So I had a separate question. Can you envision how the kernel and the libc communities might better cooperate in the design of syscall APIs? So
There's a mailing list for that.
Well, I mean, there's a kernel API mailing list, but that sort of cooperation doesn't seem to be there. And we hear via fora like this that we would prefer syscalls are defined this way or that way, and that tends not to get through to the kernel side.
Well,
That one's off, I think. Yeah, so let's try this one. Okay, so I think what worked really nicely is for some of the syscalls that were added over the last two kernel releases, just CC, for example, either like libc alpha directly, or what I did is usually Florian. And so if something goes really wrong, he will provide input. Like this has proved pretty valuable for clone, for example, the one that we did. So
Can we subscribe Florian to Linux API?
I think he is.
It doesn't
It doesn't hurt to get multiple emails.
Linux API still has a lot of unrelated traffic
unrelated to this syscall stuff, I mean. So it's quite easy to miss the key emails among very interesting interkernel.
So I think one of the things that I kind of observed is, for example, what types do you choose for from the kernel side might not be the same as what glibc is choosing in terms of types. You had something like this, but it also goes, for example, which I found out the hard way, for structures, for example. The way it is passed in the kernel, such that we can do it in the same way for all architectures. It doesn't matter if it's 64-bit, 32-bit, or alpha. Yeah, exactly. Then talking to the glibc guys, and like, these types are acceptable for us, but we need to provide wrappers and so on. If you have sizes in syscalls, use size t. Like for example, there's still sometimes a debate when new syscalls are added between are you using an integer for a flag argument, or an unsigned int, or a long, or that probably is stuff that could be sort of more standardized from the kernel's perspective, I guess. Yeah.
Unfortunately, conflicts on syscalls is the issue.
No, sure, but going forward for new ones, I mean, yeah. Sorry.
And I have a question about, I have a question about, so is glibc the place for like higher level wrappers around syscalls rather than just syscall wrappers? An example would be, there's OpenAT2 work I'm working on where the correct usage, the most idiomatic usage of it would not be to just use OpenAT2 directly, but instead would be to handle paths differently effectively. So you effectively would have like a wrapper around a file descriptor that you would then use as a handle to a file. The point I'm making is glibc the right place for that, or should that be somewhere else? Which is something that I've been battling with. Or both. Or both, yeah.
Well, my understanding is we only expect the bare wrappers without a higher level interface. I mean, you know, the higher level interface is at the sort of the C library level, and you know that's mainly defined by the ISO C committee and such.
Except of course that this is. Except, of course, this is not always true. I mean, Open Memstream et al. were glibc first, and that's very much a wrapper around a file descriptor, implemented in FileStar and so on. I think the real question is probably that it needs a lot more design if it's going to get careful design if it's going to go into a higher level wrapper, because other architectures and other operating systems might want to use it.
That's true.
It may well end up going straight into POSIX eventually. Yeah. So more care is needed. The more complicated the interface is, I would guess.
I would just like to add that sometimes it's documentation that stops adding wrappers rather than a thin piece of code. Because, well, it has been said already that it requires copyright assignment, and sometimes it's not easy to write a new documentation when a piece of documentation on that syscall already exists and the author is not interested. He just contributed this documentation along with the commit, inside the commit message, for example, for this syscall, and he's not interested, and to write a new documentation for the same thing, it would require either a new piece of documentation, which is not easy, and you can't reuse the already existing documentation because it would require copyright assignment from that person, and he is not probably interested or he's not aware of the thing. So it's like, it will require cooperation between people, and it's always not easy.
Yeah, but I think it boils down to the lack of resources, because obviously the glibc community can help with writing a piece of documentation, but someone has actually to do that, and people may not necessarily have the time to
I mean, it's not easy to write from scratch a documentation for the same little thing, and not to do the right work.
Yeah, but at least, you know, when you have a contributor, you can talk to them and sort of ask about the details in an informal way and get this formalized in this process. It's been happening before, so it's doable certainly. But I mean, you know, the issue is the lack of resources.
Right. I think glibc over the last 2 years at least, just from my observation, has changed a lot, like in terms also of how it operates, and it's, I think 2 or 3 years ago we tried to get a patch and went for this TOCTI, PTP stuff, and it took us over a year or something to get something. It was really frustrating, to the point where Florian then wrote me a mail and said, like, you should get a copyright assignment for FSF, and then you can have commit rights, and then you can push it yourself. I think like that fortunately has changed, but the word needs to get out. I think that is really a community that you can now work with. Yeah. I mean, we just got, people are really surprised when we got the MEMFD create syscall wrapper and the sysget TAD syscall wrapper. I don't know how many years after these syscalls were actually merged into the kernel.
idea has been missing for donkey's years.
Right?
Yeah. Nobody ever expected that to happen. I mean, it's a little too late now because everybody has that wrapper in their code.
Yes, yeah, for sure.
Well,
But yeah, so I think if word gets out and more people know about this, and there's even more interaction right now, and I think between the kernel community and between the glibc community, and I think if we sort of increase that and kind of everyone who's working on the kernel side of things and then keeps in contact with the glibc guys, I think this will improve, hopefully, so that we don't have to ship a libc library with LLVM.
okay, anyone? No? Okay, thank you for coming then, and we'll pass the message on to the Junior Troll Squadron later this week, and we'll do our best to cooperate.
So, just as a small comment, so yeah, just as a small comment to a question that was asked earlier about how can we do to better cooperate. Well, let's do this more often. Like
once a year? I agree.
I mean, yeah, like talking here, like before Cold Run, and and so this is, to me, this is awesome.
Well, yeah, a lot of times, for example, it's ask ourselves, or does at least help me, is who has sort of a stake in this specific work or specific system call, for example, and a lot of times it's glibc for not necessarily obvious reasons, and but asking them for input, especially from, and you have to give it to him, it's like, especially from Florian, is really helpful, and he's pretty willing to ask really interesting questions that we as kernel developers do not necessarily have on our radar, because we might have a different perspective on things. So that helps a lot. Just being also for the glibc community more active, especially on Linux API, would probably help a lot.
Okay.
So, thank you. So we are a few minutes before 11. Can we have a little break of 3 minutes bathroom break? Yeah.
Apparently, even being one chair
So,
over,
can you
there's
talk
no
to me,
problem.
please?
It's just amazing to watch you like. Seemed to work.
It's not working. Test, 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 test.
Also, it's really the microphone.
Test, 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 test. Testing, testing. Hey.
But
Oh.
this one works.
Yes.
If you don't mind to use that.
That's fine.
Okay, thank you. I'll just change this one.
You tell me when to go, Jose.
Oh, sorry.
You say yes or no? Yes. No. Okay. All right. I'll go. Okay. Hey, 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 hey. Ready? Okay. Hi, I'm Case. This was just an idea about trying to call attention to some of the security features and like security flaw mitigation work that's in various compiler toolchains now. There's a lot of work happening, especially on the Clang side, to get things up to speed for building Linux kernel, and there's tons of work happening there, and it's good, but I wanted to try to call attention and raise the priority of some general security features. So what I mean, looking back at like old school security feature examples, stack canaries and uninitialized variables and format strings, like these should be pretty familiar at this point. These are well supported, although we do occasionally see bugs in various pieces of it. But these are sort of the things that I would call we're done with on the toolchain side. And this presentation is mainly these pieces, which I'm going to go through in the following slides and get into what's missing and what I'd really like to see. There's a lot of like patches or plugins or half-working things, but I'm just going to jump in. And you can download the slides too from the first page. So I'm going to start with the easy stuff, which was per function sections. This works. It's good. I just wanted to call it out as this is an easy one. It's done. But this is mainly for the reason I've been interested in it is that it supports fine-grained ASLR. So if you have a separate section for every function, at kernel boot time, you can actually randomize all of the functions. So suddenly you get extremely fine-grained ASLR of the entire kernel because you can just randomize the section locations, which is bizarre and wonderful. One that we've been working on a whole bunch lately is the switch case fall through. So in C's switch case, you can specify break, but you don't specify fall through. You just leave out break, but that doesn't indicate if you meant to fall through or not. So implicit fall through was already in both toolchains, but Clang did not support the fall through attribute until very recently. And GCC actually parses the comments looking for markings as well. Yeah, so it was to have, GCC's parsing of that was to have parity with the IDEs and all sorts of other things prior to this being standardized. And Clang has said quite loudly that they will not be parsing comments. And the kernel is free of implicit fall-throughs at this point, mostly thanks to Gustavo's work. And like in the roughly 500 patches just in the last year alone, about 10% of those warnings were real bugs. So it was actually a pretty high number of those like actual missing breaks in the kernel. So this has proven a a good thing to turn on and a nice change to make in the kernel's sort of C dialect, in that we don't want to have implicit fall through anywhere anymore. Link top optimization, this is another one that works in both tool chains. It's required for control flow integrity because you need to have visibility across all of the functions simultaneously at one point. There's kind of a lot of pain in updating the build systems to support LTO because you don't have, you have intermediate states, you don't have actual object files as you build. And there are still questions about the differences between C's memory model and the kernel's memory model. And there are some worries that those don't match, although no one has been able to provide a specific example.
There are. It's the consumer part. There's an entire C standards document written by Paul McKenney on this issue. They do not match.
Right. Oh no, I agree. They don't match. But no one has proven that using LTO suddenly produces the bugs, and no one can come up with an example of it. I don't disagree that theoretically there's a problem.
Okay.
But the practicality is sort of what matters here. And being able to declare a way to keep people happy about using LTO in the face of the differing memory models is still something to be solved.
Yeah, so I would love to sit around with some of the actual compiler people, and then preferably both GCC and LVM at the same time, and get this sorted out. Because
right.
It's waiting for the C standard committee to get their hair entangled is just not going to happen.
Right. I would like that too. It's coming up quickly, that we're going to need to have this solved.
The C standards committee, in any way, their job is not to create. It's not to create them. It is to. The C standards job is not to create the thing that we should be using. It is to ratify what people already want to be happening. So you hope. I hope, yes. I know some of the people involved too, and they have told me that they have learned that lesson several times.
Oh, so there is that. There's the end of life. There is, what's the other one? Pointer provenance, which is an absolutely disgusting thing. There's the whole memory model thing. Dependency ordering. There is control dependencies, which C does not do. There's a number of other things, but basically, I'm scared of compilers.
Me too. Yeah, so anyway, there's work to be done, not in necessarily LTO itself, but in resolving the visibility and the memory model issues. Stack probing was added to GCC. Clang still lacks this. This was, as you use a VLA or alloc A, you'll actually read the stack in small byte offsets to verify that you actually can get to that mapping. From my perspective, this is now only interesting for user space because the kernel has completely eliminated the use of VLAs and alloc A. And in the year that we took to do it, systemd had 2 exploitable alloc A vulnerabilities. So it has been my strong recommendation that nobody use VLAs. What?
To not use systemd.
I'm not going to stand here and say that. But you can have a mic. So again, this is another case of effectively changing the dialect of the kernel using the options that we've got. But if you must use VLAs for some reason, having stack clash protection turned on is nice. Then there's Spectre v1 mitigation. In Clang, this exists as the speculative load hardening. The performance impact is pretty high, but it's better than using LFence everywhere. And I think it's needed in GCC, but maybe I'm going to get corrected.
Is it the heuristic that mostly works, or is it solid?
My understanding is that it's solid, but that's why there's kind of a large performance hit.
If I could just note, stack clash protection isn't just needed for VLAs, although VLAs are an extreme case. It's needed for any function call with very large local variables. So you can't avoid it just by not calling allocate. You have to avoid it by bounding the size of your local variables to be less than a page, which seems a little inconvenient for the general case. Stack clash protection is easier.
Yes, so having large recursion, for example, you have an issue with that. This is less of an issue in the kernel.
Yeah, using a page worth of on-stack data is an absolute no-go in the kernel. That
Oh,
just
yeah,
that
this is a user space problem.
Yeah.
Right.
In user space, it's still quite valid, which is why it's good to have it in all the tool chains. So we don't recur this flaw again. Anyway, yeah, so another note about the V1 mitigations is, I believe in looking through this, there's a function attribute you can set. So you don't have to globally enable it. You can globally enable it, but you can also do it on a per function basis. I still want to spend more time looking at this. This is an interesting one that's in the Clear Linux patches to GCC. So this is a patch only, but to an older GCC. This doesn't appear to be landing upstream. It would be nice. There's nothing like it in Clang at all. But the idea is to wipe all of the callee saved registers on return, which has a surprisingly small performance impact because XOR of the register itself gets pipelined away very, very efficiently. The idea here was this was designed to keep registers as clear as possible so they can't be used for leaking data in and out of all kinds of things for side channels and other stuff. So to me, this was a low performance hit, easy thing to do, but it requires some internals at the architecture level to enable.
So I know we do register clearing on system call boundaries, but what exactly does this mitigate in kernel across every other function call?
I think we should ask Arjen more specifically. He was the one driving this change, but it seemed like to me, it seemed like a low-cost way to just say, now we don't have to worry about those registers anywhere.
Yeah, so I'd love for some of these security features to actually have a proper description of what we're mitigating for. I mean, it's a low cost, but it's still a cost. I mean, it's a death by 1,000 cuts, and if it doesn't actually help anything, we really shouldn't be doing it.
Well, the argument was we end up with a lot of side channels through side effects, and trying to control as many side effects and to bring as much of the architecture into a known state at a regular basis reduces how much or where the leakage can happen, even when we don't know where it's going to show up next, which is sort of a weird, scattered approach to trying to solve it because we don't know what's coming next as we are beaten over the head with side channel after side channel problem. But perhaps the poor justification is why it's not in upstream.
Well, this would be mainly a concern for handwritten functions, right? Because otherwise, it would be like a compiler bug, basically. I mean, Calais saved register, they should be saved. And the code generated by the compiler should be assuring you that.
Well, no, this is, so if it's callee saved, you don't have to do anything with it. You can just return, and you can leave whatever state was in your registers. Yeah. The idea is just wipe everything that got touched in that function.
Okay.
Just wipe out the registers completely, so there's nothing left over.
And what's the status of that patch?
No, clobber.
Clobber. Okay. Yeah.
Sorry, yes, I should rephrase that slightly.
I was a bit confused.
Sorry.
Yeah. And what's the status of the patch? Has been it submitted to GCC patches?
I couldn't find it anywhere. I couldn't find it submitted anywhere, and it's against an older GCC. So I'm not sure why it hasn't gone anywhere.
Okay, so we should do something about it if you want that in.
Okay.
Yeah.
I'll go poke Arjen some more. So this is another C dialect desire in the kernel, is to have stack variables auto-initialized to 0. We're most of the way technically in Clang with this. There was a lot of debate over not wanting to support zeroing of stack variables because it was viewed as a language fork. Because now you can depend on your stack variables, if you don't initialize them, as being 0.
And this very much includes padding and holes.
Correct. That works in Clang. Linus has been pretty explicit about wanting it to be zeroed, not just not uninitialized. So Clang's implementation right now adds a bit pattern instead of zeroing, which is fine for avoiding uninitialized variables, but it's not great for how Linus sort of views the future of that kind of thing. There was a patch a couple of years ago from Florian that didn't go anywhere. There were some conflicts over, well, do we no longer get uninitialized variable warnings now? So there was an idea of wanting to split auto-initialization from unused variable or uninitialized variable detection, and still being able to warn about it even though it got zeroed, and there were complexities about that. There's a plugin in the kernel that does the initialization, but it's pretty late in the compilation process, so it ends up doing some bizarre tricks that confuse other things like KSAN and stuff like that. It'd be nicer to have this natively in the compiler, happening at an earlier stage, that it can be correctly optimized throughout the process. So yeah, starting on this and finishing the getting the 0 as an official thing in Clang is pretty high on the list. But at the very least, we can do it in the kernel and get stack initialization.
Wait, sorry, does Clang have it, or Clang doesn't?
So Clang has the pattern option. So I can say, hey, if you're building with Clang and you turn this on, now you don't have any uninitialized variables on the stack. They are initialized. They are not zeroed. So they have the hex AA pattern in most of the bytes, depending on your architecture, the type that's there. Like, it's an incredibly complex set of things that they want to do. Yes, exactly. I don't understand. And the kernel has a pretty large set of tests for this, looking for padding and other things. And so all of that gets initialized. Anyway, so getting this, I talked about this last year, trying to get a foothold on this. Anyway, so yeah, I think the main argument to just make sure it's up in front is, like, this does fork C. Like, suddenly you do have, like, stack variables are 0 if you don't do anything to them, which is a pretty radical change.
I suspect trivial specifically means don't expect this to work for C++ classes, which aren't plain old data, or something like that.
I don't know, but I'm pretty sure it does cover the C++, knowing the people who were involved in it. But I can't say for sure. I haven't looked at that. A delightfully insane feature is the structure layout randomization.
I hate it.
It's for really paranoid builds. There's a GCC plugin that does this, and Clang has a stalled version of this that was done as sort of a port of the GCC plugin.
It's good for that.
But ultimately, it's just an attribute on structure definitions, and you get a randomized based on, you can have a seed in your build tree. So if you build multiple times, you can have a static seed, but if you blow that away, you'll get a different layout of the structures that you've marked. The plugin also has a mode where if your structure contains only function pointers, it will randomize those automatically, which I think in the Clang port was a separate flag. Anyway, this isn't, in my view, needed, but it is really fun for paranoid builds because it changes target layout from the attacker's perspective. You know, why have kernel ASLR when you can have like code ASLR?
It does slow things down. I did some checking on a really old piece of hardware, and it slowed it by about 5 to 7%. Presumably because all the cache optimization and so on has been blown away.
Yeah, so the plugin, the way it was written, you can have a performance mode that doesn't randomize outside of a cache line, which is interesting, but it's still completely insane. It's a lovely feature. I could spin it as it's good for debugging. We found some interesting problems with it. Signed overflow is technically an undefined behavior, but you can specify it being defined.
We all specify it as being defined. It's
Yes.
two complements, the
Yeah,
end.
Yeah, so in the kernel C dialect, we have defined this as just wrapping. But it tends to be unexpected behavior. There are places where we wrap. I haven't found any intentional signed overflow outside of like the reference counter stuff, but almost always you don't want the result from your signed overflow. This can be, you can actually add the test for this. This works in both toolchains. If you just sort of fail, it's awesome. Like there's very little code size change. There's very little performance change because it's a flag test, and that just disappears into the cycle counts. So it's runtime wise, it's fine. However, when you turn on actual warnings so you can get meaningful output, your object size increases like by 6% just from all of the strings that got added, describing to you all the places where your potential math has overflowed. I'd really like to have this be a user-defined handler where we could have an explicit exception, like sort of like bug and warn use already, and then we can just say, oh, it happened over there, and we don't have to have a massive text size change. Another piece is right now there's the die mode where, oh no, I've overflowed, kill everything, which is not helpful, or warn and continue with whatever the bad value was, which has wrapped around. I'd really like to have a warn but continue with a saturated value. Like don't actually wrap, stop at a large, at int max or whatever. Because most of the time if you're passing it to an allocator, the allocator will scream at you and you'll actually get an error path as opposed to getting really strange results. Very similarly, there is unsigned overflow. The kernel does a lot of legitimate unsigned overflow. So finding and marking those is something that needs work in the kernel. On the toolchain side, Clang has the ability to do this, the same instrumentation as assign, but GCC does not. I haven't looked into why. I assume it's relatively similar. This one is not technically undefined behavior, but it frequently leads to exploitable conditions and things that no one wanted. So again, getting this saturated behavior would be nice because then we'll actually be able to catch the errors and continue as opposed to getting small allocations that get overwritten, et cetera. I'm going to start with hopefully the easier of the two CFI types. So backward edge CFI, which is testing when you return that you are going somewhere you intended to go. The hardware support for this is where most of the work on this exists in the toolchains. So on x86, there's the CET feature bit, and this basically just in the CPU becomes an implicit, it happens implicitly on call and return, so there's actually no compiler support. You just need kernel support and OS support for it to set up the second stack, like you end up with two stacks. On ARM64, this works by doing pointer signing, but right now in Clang there isn't an attribute to turn this off on a per function basis. You can only turn it off on a compilation unit basis, which is rather awkward. And there are special places where you want to turn this off, like say all the code that initializes pointer signing. You don't want to have signed it because things go crazy. There is a software implementation of the shadow stack. It's on ARM64 only in Clang. It did exist on x86, but had performance and other problems, so it was actually removed. So I think the thought is just waiting for hardware support there. But it would be nice to have a software shadow stack in GCC as well, since it would be nice to use it in the kernel, but I know this would be useful in user space as well. Forward edge CFI, so protecting indirect calls. You know, you've saved a function pointer in the heap, and you read it back and jump to it. Actually validating the destination of those is another good one. So in hardware, there's really only support for coarse grain validating that you're entering a function. So as an attacker, the attack surface has been reduced from all of the bytes that are executable to all of the functions that you can reach, which is a huge attack surface reduction, but tends not to actually be practically much protection, because you can just chain functions. That's already what a lot of attacks were doing anyway with ROP. Anyway, there's support for this. The x86 and AMD 64 versions of this already in both the tool chains. In software, to do this for fine grain, in other words, allowing an indirect function call to only call other functions of the same function prototype. That's sort of the bucketizing that was done for fine grain CFI. This works in Clang. It would be really nice to get this for GCC, as fine grain CFI really is important for getting protections going forward. The paper I linked here is sort of a one-click exploit generator, because you can just automatically chain together all the gadgets you need to perform the attacks, and CFI completely stops this. Or rather, makes the possibility so much smaller that they at least can't be automated right now. So anyway, since we have LTO in GCC, it would be nice to also gain the CFI features, since we have the visibility available to do it. And that's my whole list, which I'll just go back up to as a reminder. Anyway, that's it. Those are the things I've been staring at and hoping to get help with. Any questions? Peter.
I'm lousy with balls. One of the things that kind of occurred to me was, and I know already, I know everyone is going to absolutely hate me for saying this, but once you're talking about like introducing integers with different semantics, because that's what you're asking for, you're starting, and then having customizable behavior for different kinds of overflow conditions. That's starting to sound an awful lot like something that would be a hell of a lot better done in C++. Because that is what C++ does.
Yeah. I'm not sure it's much better in C++, I think is what I would say. If you're talking about catching exceptions, I still can't, even with C++, like I can turn these on for C++ and I still can't saturate the value and carry on, right?
Yes, you can. You can define a class that does that. And that's the whole point.
That ends up having a significantly larger performance impact. This right now is a flag test. It's a single instruction.
Yeah, you can
it jumps to a cold section. Like
you can do that.
Okay. I think it will be easier to fix these call sites up in the kernel than to switch to C++.
That wasn't nervous.
Yeah, in the meantime. I have Rust modules loading.
Yeah, Rust has this. You can do saturated add in Rust.
Except in the first chapter of the Rust book, it describes overflow behaviors, and if you're building in production and not on debug, it wraps.
But Rust doesn't have a memory model, so it's useless.
Oh, I'm not even going there. I just like.
There's a saturated add method. Like, if you do plus, it will wrap and so on and so on. But if you want it to be that,
Yeah. But it has atomicity issues, the condition bit and taking the exception. So really what we need is different integer types in hardware.
Okay.
No.
I mean,
x86 has saturated add instructions and that sort of thing, doesn't it?
I didn't find them.
I don't think so. If it does, that would make things easier. Yeah, no, I'd love it if we could just get rid of integer overflow class of bugs. That would be nice if I had a hardware integer type that would not do that. Anyway, keeping you from lunch or a break or something. Cool, thank you.
Thank you. All right, this talk is going to be on Clang-built Linux, and it's essentially going to be an update of the Linux kernel port to Clang. Now, this is a project I was a part of more in the past. It's not something I'm directly working on anymore. However, Nick Desaulniers from Google, though the major contributor now and the fellow that basically is driving much of the rest of the work across the industry, he had more important things to do this week and couldn't actually make Plumbers. He's at Iron Maiden concert. So anyway, it's not that he doesn't love you all and doesn't want to be here. It's just that there's more important things going on. Maybe. In any case, so what happened essentially is that in order to do this conversation, this talk, I basically got a hold of Nick, and we got onto a Google Meet conversation, and he basically did a brain dump, and this is the result of that particular brain dump. Now, the first thing first, and this perhaps isn't entirely useful for everybody here, but just to make the slide deck come out, is the first question we almost always get is, why use Clang? Why bother? We've got a perfectly good compiler with GCC that we've always used. The kernel's brought up on it. It works perfectly well with that. Why would we possibly spend the time getting Clang working? And the major issue these days isn't what we used to say. In the past, it was because Clang had certain features that GCC didn't and so on. There's largely feature parity in many respects these days to those complaints. These days, the number one reason is generally because some companies want to use a single compiler across their entire project set. And to a certain extent, certain companies have decided they would prefer to go with Clang for various other reasons over GCC. And so when it comes to actually extending and fixing problems, they want to do it with, on a single compiler as opposed to two of them instead. The other thing, of course, that's very good is that to a large degree, when it comes to things like the C standard, most people don't ever read the C standard, right? Just a show of hands, who here's actually read the C standard? Okay, that's actually a lot better than the last time I did this. Now, the next question is, which version of the C standard?
All of them?
Okay, who's read all of them? Okay, so a lot fewer hands, right? The reality is the vast majority of people think they know C. What they really know is write code. Does the compiler say it's okay? Yes, okay, continue. Okay, and even for those who have read the standard, have you read it all the way through, or have you merely read parts that you need to read? And unfortunately, I only read the parts that I need to read, right? So the reality is that the vast majority of us don't know C, and then beyond that, we don't actually use C in the kernel project. In fact, we use a version of C. We use the C variant, the kernel variant of C. And so one of the nice things about using two compilers is because standards are interpreted by the people who write the compilers, it's a good idea to have multiple versions. I think we just lost audio. Yeah, I was pretty sure too. It's a good idea to have two different interpretations of that specification so that we can actually make sure that they match. So by having two compilers do the same work, in fact, we actually find those places that are otherwise considered to be undefined behavior.
Because in the past, at least, from what I found when I did a lot of my work with Clang, in fact, was that the kernel in certain situations was actually depending on undefined behavior on different architectures. And so by having two compilers, we can actually find those things a lot more easily. Certainly a number of the areas where that's been a problem from a security perspective, cases actually managed to find and get rid of. One of the big ones, of course, being VLAs and VLAs and structures. The other thing is, in fact, the work on getting Clang to work with the kernel has had another effect, and that is, in fact, to improve C support in Clang. It turns out that Clang is extremely heavily used in both C++ and in Objective-C, and in those particular areas, it's very well supported and well tested. On the C side, it's in fact less used than for those two languages. So in fact, getting it to work with the kernel being one of the largest software projects in the world, in fact, has made it better overall. So in fact, it's been a net benefit for the the Clang project as well, which is very useful. So this has probably got to be the biggest problem that people brought up, certainly towards the end of the time that I was doing on using Clang with the kernel, and that is the support for asm_go_to wasn't available in Clang. And asm_go_to is very important for being able to enable things like config jump label, which allows you to optimize the use of fixed predictions of whether you're going to go of a particular have you. Asm added to Clang, and in fact has been tested very heavily with the Linux kernel, which is very helpful because, for instance, amongst other things, config jump label has now been made mandatory in the x86 kernel. So it's something that was actually absolutely required. Interesting thing, of course, that asm_go_to, though well tested with the kernel because of the companies that are now using asm_go_to with their kernels, it's actually less well tested in user space. So for non-kernel targets, in fact, asm_go_to, in fact, still is a work in progress in certain situations. Oh, somebody have a question? I'm not sure the mic is on.
So, it's on.
Yeah, it's on? Okay.
Yeah.
Okay, so
hug the mic.
Yeah, we found a number of interesting compiler bugs while asm_go_to was.
Oh, no doubt.
Yeah,
No doubt.
yeah, that was fun.
Yeah, compiler bugs are always fun.
Yeah.
But yeah, this is one of those areas where it was a long time coming, and it was a long complaint that it was not supplied. And in fact, I was asked for this over several years as to when it would be added. So that does not surprise me. The next one is inline assembly. And there's two levels of inline assembly with Clang. And those two levels are, first, Clang needs to be able to parse inline assembly, whereas GCC largely is past the assembly verbatim, so it doesn't have to understand it. Because Clang has integrated assembler, it actually has to understand any inline assembly before it passes it off to the assembler, whether it is an external one or an internal one. And some of the formatting that was used was specific to the GNU assembler. And the problem is that a lot of those things were extensions, and extensions that were not a part of any kind of standard. And in fact, they were often extensions that even the GNU assembler people basically didn't think that Clang should in fact implement because they were just too out there and basically unsupportable. Things that people are already using, they couldn't remove them themselves, but they sort of wish they hadn't done some of those things. As a result, support in Clang has been very difficult in areas. The nice thing is that the Herculean task of changing the assembly in the Linux kernel to be more standardized, a lot of that has been done now. So it depends on the architecture exactly. For instance, Stefan Eigner has spent a long time fixing up the assembly in the ARM architecture to bring it back to the unified syntax, which is very good. And indeed, a lot of the extensions that were part of GAS have slowly been removed from the Linux kernel to make things a lot more supportable. So that's really good. Unfortunately, the integrated assembler still can't be used, so the speed-ups and the debuggability that the integrated assembler brings to the table, unfortunately, still aren't possible. However, that still is something that people want to do going forward to be able to make that work. And another question here. I think it should be on now.
Yeah, okay. So the integrated assembler, does that mean that Clang can change our inline assembly? Or does it guarantee that those exact instructions will be emitted?
Integrated assembler essentially is just another path within the compiler. It basically means that instead of forking out to an external assembler, it actually has an assembler built into the compiler itself. So the whole point is that it can, for instance, in the event of inline assembly, just having a single instruction, it will just emit that single instruction and continue.
Okay, but it will not then interpret that instruction, put it in the intermediate representation, do optimization passes over it, and emit something else altogether, which has seemingly the same effect.
I understand what you're saying. As far as I understand it, it basically goes, my understanding is it goes straight to an instruction. I don't believe it goes through that path.
Okay, so because we very much rely on specific instructions to be emitted in a number of places.
As far as I know, I'd have to double check, but as far as I know, it emits an instruction.
I can confirm, yes, that's the case. The separate path.
There we go.
And, instruction will be preserved.
Okay, yeah.
Excellent. But it does parse them, so it knows to change control flow and that sort of thing.
The comment was that it does parse the output, so it understands the control flow that it brings to the table. And yes, that's agreed. The reality is that Clang is supposed to understand certainly the encoding and certainly what it's trying to do and so on, but it will emit the instruction. However, at the moment, it's not possible to use it for various other reasons. It's just that we're getting closer to being able to do that now, which is the ultimate goal. And basically, the support for understanding assembly is something that is an ongoing affair, and certainly different encodings and output parameters and so on have been added to Clang's support of inline assembly over the years, and so that's taking us closer and closer to the point of being able to enable the integrated assembler. The next one that we should maybe talk about is LDD. Now, the compiler itself, of course, is one thing when it comes to actually the support surrounding the compiler, the rest of the tool chain, things like the linker, the debugger, the assembler. These things all come from binutils traditionally, and indeed binutils has been a big part of having to use Clang still. Of course, binutils is a separate project from GCC. When it comes to Clang and LLVM, they have their own equivalent of all the binutils utilities. The big one that people have really wanted to see for a while is something called LDD, which is the linker that came out of the LLVM project. Now, this is actually kind of interesting because one of the major things that LDD is very good at is things like LTO, for instance. And it does this in a very heavily threaded manner. So whereas LD and Gold are quite linear because they're not threaded, LDD is heavily threaded and therefore tends to actually get to an LTO output that much faster, or at least it tends to link faster, especially in a incremental linkage situation. Now, LDD has been something that's been very slow to be worked on over the years, in part because Gold did most of what it needed to be done. However, again, there are certain companies that desperately want to move to something that is all LLVM related, and as a result, work has been put into LDD to the point now where, in fact, there are products that are getting ready to ship later this year that are 100% LDD linked, and one of those is the next version, or very likely one of the next versions of the Pixel. I don't know which one, but apparently one of the Pixels later this year will be shipped 100% with LDD linked kernel. Otherwise, sorry? It's LLD.
Oh, okay.
Yeah. There's also LLDB, which is the debugger. Unfortunately, the names are hard to say, and it's like LVM and LLVM. People get those two mixed up as well. The namespaces collide very. Sorry? But yeah, otherwise LLD basically does essentially what Gold can do. It's just an entirely different code base and, of course, a different license. And sorry, what?
Yeah, so we removed Gold support from the kernel.
That's true. I saw that recently. That's true. And why was that? I don't. If I looked into that.
Because we ran into various bugs, and the binutils people basically said linking the kernel is not a priority for us. So we said, well, then you're not for us either.
I hadn't heard that part, but I didn't see. That's true. Gold had moved recently. So, okay. Well, hopefully LLD can do similar things then. And now LLD, in fact, just being a generic linker, in fact, it does not have to only be used with Clang. In fact, it works with GCC as well. But of course, in this instance, the idea for Linux is eventually to have it, of course, compiled, assembled, and linked all within the same tool chain. The next thing is adoption of Clang, and this is something that changes over time. Now, the really interesting part was back when I was doing this more heavily, and I was trying to work with Google in order to get them on board to help port the kernel to Clang. Clang was being relatively heavily used at the time for things like Android, and they were starting to look at it for things like Chrome OS. But on the kernel side, in fact, it was less interesting for many people. And overall, their move forward has always been, in fact, towards Clang. And so in the last couple of years, one of the reasons why Nick got so involved in it was because essentially they wanted to move Android, Chrome OS, and other things 100% to Clang. And so generally speaking these days, Google has moved largely away from GCC and binutils. And to a large degree, what they're finding is that there's a long tail of features that need to be fixed in things like Clang, in the IA and other things, in order to get feature parity or for that matter, bug comparity with binutils and GNU AS. And so the first thing, of course, is talking about Android. Android, in fact, had largely moved away from GCC to Clang several years ago. Getting it to work on the kernel was one of the major last things they needed to do. And these days, they've basically moved away from Clang almost 100%. The kernel was they do have a couple of things that still use GCC, but they use a very, very old version of GCC that they have instrumented to make work appropriately. They're not planning to upgrade that. They want to move over to using Clang instead. Android Q these days, the one that just came out, it mandates that their OEMs use Clang to build kernels. So basically, if you've got an Android Q device, in theory, its kernel is now compiled using Clang. The major reason for this is that they want to make sure that there's a 100% guarantee that the ABI between user space, Android, and the kernel is 100% the same. And so for debuggability and other reasons, they're mandating that Clang must be used for all Android kernels now beyond Android Q. What this basically means is that all companies now trying to support Android into the future, of course, will be mandated to use Clang for their kernels. To the end of making sure that the ABI is in fact stable and in fact it basically works across all platforms. There are now people using something called libabigail that allows the testing of binary ABIs to make sure that the appropriate thing happens. They're basically trying to make sure that the ABI doesn't change over time or between versions of the kernel, or indeed, ideally, between GCC and Clang. But to the large degree, they're trying to make sure that the Clang ABI for their platform basically stays the same. To make this easier, one of the things they've now done as well is they've shipped a new dev platform. It's called Cuttlefish. It works for x86-64, and it allows you to essentially do debugging on your development device without having to go to real hardware. It's all 100% Clang built as well, including the kernel, obviously. Chrome OS, same deal. They've moved 100% to Clang. They now have all targets x86-64 and ARch64 are now Clang built from the kernel onto user space. ARM32 still has a couple of issues that they're trying to work through, that they're not entirely there yet. But ARM32 being less of a platform for them these days, it's been deprioritized, is my understanding. But pretty much, if you've got a Chrome OS device, it's running a Clang-based kernel now. This one surprised me, and that is that Google Cloud servers are in fact moving over to Clang as well. There had been a problem in the past supporting kexec, and that actually had stopped the moving of services over to Clang. However, that's now been resolved, and they're now in the process of doing some pretty heavy testing to move the rest of the Google Cloud services over to using Clang-built kernels. Just in general, my understanding is that Google has actually managed to debug and find a number of fairly major errors by compiling with Clang in the past, which has led them to actually want to move everything over to that otherwise. And I think we've got a question here.
It was just a statement. Yeah, this isn't just cloud servers. We're trying to move all kernels.
Sure. No, I can't say that. I'm just passing on what was told to me. That my understanding is that everything
I'm adding to your slide.
There you go. So there you have it. So Google's trying to move everything over to Clang. That's more or less what I had understood. So, but thank you for clarifying. The next thing is LTO. Now, LTO is something that a number of people, probably even in the room, have been working very heavily on for years. LTO is now something that certainly is being used very heavily within Google. The Pixel 3 apparently and newer will mandate the use of LTO using Clang and LLD as far as I know. Android R will be shipped also with LTO Clang kernel, which is very interesting. So it didn't come out in Q, but will be coming out in the next version. The idea effectively is once they have that working, that it will also be upstreamed to make sure that, in fact, LTO support is pushed upstream. Internally, they now have x86 64, ARM32, AArch64, PowerPC 32 and 64. And last time I talked to Nick, they had just got MIPS 32 working. So that's pretty interesting to be able to have an LTO kernel across all those architectures. And my understanding is other work is being done in other areas. For instance, apparently also messed around a bit with getting it working on Spark and System Z. Not really sure how far I got on that, but apparently some work has been done there as well. As far as LTO support, apparently they are going to support versions 4.4, 4.9, 4.19, and standardized kernels that Android currently mandates. As far as testing, this was probably one of the things that I was happiest about when it happened, because it was something that I hadn't quite managed to do myself, and that is there's now a full CI build tester on both Travis, but also within kernel CI, which is quite nice, now using Clang, which is great. The other one that's kind of awesome is the zero-day bot from Intel is now actually also supporting a Clang-built kernel. However, at the moment, it's private only for Google, in part because it's still very noisy. It still has a lot of warnings and other things in it that they're slowly working through, but they're really hoping that they can make that more globally available once they reduce the noise on it. The last thing that everybody here wants to see is a million errors and warnings coming out from a compiler that they're not strictly using themselves at that point in time. So right now there's support for ARM and AArch64 that's in testing, and x86-64 is actually still a work in progress. So there's still some work to be done there, but the nice thing is that there is more automated testing, even more so than what we were running back when I was doing the project. Of course, the other thing which is both good and bad is there are different warnings between the two compilers, as one would expect. This essentially can show where there are potential problems in understandings or the possibility of undefined behavior and other things like that. This is one of those situations where different people have found errors basically by trying different compilers to see what the output happens to be. The testing in the case of Travis CI and kernel CI is both building and booting of the kernel, so it's not just a build test like the zero-day bot. They're actually doing full boot testing as well to make sure that the resulting kernels actually do something useful. This was actually noticed the other day on the kernel mailing list. They actually also added the Clang-built Linux mailing list to the maintainer's file. If you look carefully, in fact, it's instead of specifying a file, in fact, there's a pattern in there that basically says if the file contains the word clang, messages should head over to this mailing list. So basically, the clang group has more or less added themselves as maintainers for any file that claims that there's some sort of clang aspect, which is interesting. So the good thing effectively is if there's a clang related problem or a clang adjacent issue, the appropriate people will be emailed, which is quite useful. So at the moment at least, the right people should be told if something doesn't work, or if indeed an update to a particular problematic file essentially that's being made for GCC, they can basically see whether it's going to break clang or not. So this list is by no means, this is not a list of every company that's using it. These are some of the major ones that Nick is currently aware of people using clang heavily, certainly on the kernel side. And this is companies like ARM, obviously Google, Intel, Linaro, Qualcomm, and Samsung. That's not that all the work that these companies are doing are on clang. It's merely that each one of these companies is doing some work on clang with the kernel. Certainly there are people around that have been very heavily involved with it. People like Arndt and Will Deakin and other people like that have been also helping. Case, of course. Other people have been working towards this work as well. The next thing is it's worth noting that there's a public meeting every 2 weeks. Essentially, there's a Google Meet that happens on a regular basis. There's a Google Calendar on the Clang Built Linux GitHub.io website that will tell you when those are. And indeed, this is the Google Meet video chat that happens every 2 weeks. At that time, essentially, all the appropriate people get on and talk. Everybody's welcome to be a part of that. And what's going on. To a large degree, it's Nick telling what's happened for the last week. Anyone who's been to the meeting, it's basically rapid fire machine gun talking from Nick to everybody else, but there's an awful lot of great information, and it's a really good place to find out what's going on and what's important to the group of people that are there. There's also a list on the wiki of past talks. Now, these are primarily past talks that Nick has given over the years on this topic. I actually need to go in and add some of my talks and some of the other ones that people have done on here so we can have a complete history of everything. But there's all sorts of talks like this one that are up there that can show you what's going on and what's happened in the past. And otherwise, this is how you can get more involved if you're interested in what's going on. There's the major website. Yeah, I know, lots of URLs. There's the GitHub, where the Clang Built Linux code is actually stored. There's the wiki. There's an issue list as well there that on GitHub that people maintain, as well as the mailing list, and of course the IRC channel on Freenode. Now, all this information is available on the first link, so don't think you need to copy all these things down. This talk, of course, will be uploaded appropriately to the website, as well as the wiki list of talks here that I showed you. Other than that, are there any questions? Okay. Thank you. Thank you very much.
We are on time. We are on time.
I'm not. It's not my decision. It's not my decision. That's their decision.
I mean, I think that very well done, but
It's a bit. I don't just happen to be a bit obvious. I don't actually agree. I don't actually agree. I actually use both compiles, so it doesn't matter to me at all.
I have so much fucking stuff. I have not been doing that.
and I think
Final address space, that's good. Yeah, I already have to go. That's 15 minutes. And that's them
Testing, testing, testing. Oh. Testing, testing.
I refuse to go here. What?
Does this microphone work? It's astounding. Okay. As Mathieu said, I think it was earlier in the day, this is in fact the first talk presentation I have given since I was about 21. And I'm already doing better because I hadn't had a panic attack yet. So, this is all. I'm sorry, I've got to look up there because my screen isn't working. This is all about CTF, and I suppose I should first say what CTF isn't. This is not the common trace format, which has been described in other talks. It's not capture the flag. It's not Microsoft security hole-filled common text framework, and it's not continuous tube feeding. We really need a different acronym, but no one can think of any which doesn't also expand to CTF. This is the common type format, or perhaps compact type format, or common ANSI type format. It came from Solaris, and they use all three different acronyms in different places. I normally call it the compact C type format because at least it says what language it's related to. I'm sorry this text is much smaller than I thought it would be on this screen, but I'll run over it anyway on the basis that no one can read something that's that size. Its purpose is to be a complete model of the C-type system, much like, say, BTF. Every type you see in a C program should be represented in it, and all the links between them should be correctly modeled. We also have try to map ELF function and data symbols into this dictionary, so that you can tell that, for example, what the types of a given data symbol is, what the return values and arguments of every function are, and you can chase down the structures and pointers to structures and so on and so forth indefinitely. This has been around for a very long time. We're finally sort of cleaning it up and upstreaming it. There are patches under review for GCC to generate CTF sections in object files. There are patches. There is already a library in binutils which can read this thing and generate this thing and merge it together and so on and so forth. There are linker patches under review. When I say under review, I mean I was replying to review comments just before this talk. And there are patches under review for GDB to use this when Dwarf isn't available. I hope it's more usable for more things than that, and there's more about that later. The CTF section does not get stripped out of binaries, unlike Dwarf. It stays in there. It's not a loaded section, but the idea is it can always be relied upon to be present. So compactness is very important. At the moment, it's about 2% the size of the debug info, of the dwarf debug info. This is before we have a working deduplicator. I expect it to be significantly smaller once there's a working deduplicator, and there are improvements we can make to shrink it further as well. We have deduplicated the kernel with a previous deduplicator which reads dwarf and turns it into CTF. The amount varies depending on the kernel configuration, but for our enterprise kernel with 3,000 modules and thereabouts, it comes to about 5.5 to 6 meg. It was originally about 6.5 meg. With format improvements, I dropped that to 5 meg in just the last 2 weeks, and I expect it to fall further. This is compressed, so uncompressed it would be bigger, but not enormously bigger. It's much smaller than the dwarf would be. I estimate about 100 meg or thereabouts down to, okay? Sorry? No, there is no support for anything but top-level types at file scope and file scope types and variables. Things inside functions aren't supported. No, also non-exported symbols. Everything. Yes. Well, no, even every type which is declared at the top level, including things which are static, gets pulled in. Otherwise, it's not much use for debugging because the public stuff is going to refer to the stuff which isn't public. In general, the libabigail people were saying we want everything. It's the same attitude for me. If I could do things inside functions, I would, but at the moment I can't. More about that later. Most of this is provided in a library, is implemented in a library in binutils, libctf. There is some code in the linker in LD itself and in BFD, but that's only about 1,000 lines, so adding to gold and so on is perfectly possible. I don't know about adding to Clang because that leads into license hell, so it's kind of above my pay grade. I don't want libctf re-implemented. I'd much rather have it be reused, but that requires people thinking about licenses. I don't know. There is a spec. At the moment, it's only for the latest version of CTF, but I plan to add everything else, including library APIs, and turn them into man pages. It will land in binutils. It's in tech info. And there's a link to the library itself as well. I thought I should compare it to things people might know about. Solaris CTF is notable for having been around for a very long time. It was the parent of all these other formats. It's a direct descendant. I changed the magic number, I changed the section name because I've changed the format. We have more sections than Solaris CTF. In particular, we have a section which maps strings, arbitrary names, to types, which can be used for things like the kernel, which has where you don't get the data symbols from an ELF symbol table, but from somewhere else. We dig them out of Kale sims, and then you can use CTF to look up the name of that symbol and that sort of thing. We have much higher limits than Solaris CTF, 2 to the 32 types. The strutab size can be that size as well. 2 to the 25 struct union or enum members provided, which is way higher than the C standard allows. But it's also the problem is that existing things like the kernel can have very large structures and very large enums in them. We've seen enums with tens of thousands of members in there. We'd like to be able to represent them. So as long as I was raising the limits, let's raise them all the way. There are a lot more type kinds. I was actually wrong there. There are 64, of which 14 are in use, so we can add new types of type fairly easily. There's plenty of space for expansion. We have bit fields in Solaris CTF were never quite properly designed. It supports float bit fields. If you've never heard of those, that's because they don't exist. But it doesn't support enum bit fields, which do exist. I fixed those with a new contraption called a slice, which sits on top of existing integral types and changes their width and offset.
Does it normalize those any? Because do you have the ABI problem, or does it get rid of
We
the
are
ABI
going
problem?
to. These are all going to be aggressively deduplicated. If you've got
no, the normalizing bit field order and things like that, because right now the C standard is wildly it's all implementation defined.
We are representing whatever, because nothing is using bit fields at the moment, no consumers are using bit fields because they didn't work, we can more or less pick that arbitrarily. I don't, at the moment, because they don't work, we are more or less doing whatever Dwarf does, but I would agree it's incredibly annoying, so it would be nice to do something else. I mean, the from Dwarf thing actually had to walk backwards in order to get the bit fields in the right order. It was ridiculous.
And we have as a minor thing, we have an archive format which you can use to take multiple these CTF dictionaries and slam them together. And we use these to handle multiple translation units. If you've got multiple types with conflicting definitions and so on, most of them land in one giant dictionary, but the ones with conflicting definitions land in tiny dictionaries descended from the giant one per translation unit. The parent-child relationship thing again, which is quite useful. A BTF, I thought people might have paid some attention to that as well. There are a few more differences between BTF and CTF because BTF is derived from Solaris CTF as well, clearly, but is a cousin of it or something, but has simplified it and thrown out some of the things that we kept. CTF has parent-child relationships, so you can have a container, a dictionary which depends on another dictionary and inherits all the types from it and adds more. And BTF doesn't have that. CTF has kept floats. BTF has obviously thrown them out because there aren't any in the kernel. CTF doesn't have a function prototype type. We have function pointer types, but BTF has a function prototype type in the header file, which includes a name for every parameter. This seems really useful, so I think I'm going to add that to CTF. CTF can share string tables with the containing ELF object to shrink its internal string table. This can sometimes be quite a dramatic shrinkage. Obviously, BTF can't do that because the kernel doesn't have a string table, so there was no point keeping it. And CTF is older than BTF, but I think they're both changing pretty fast at this point. I started making major revisions to CTF about a year ago, and I don't plan to stop. I do have a backward compatibility promise. All old CTF file formats will always be readable by libctf. I also hope, I'm talking about this on a later slide, to be able to read original Solaris CTF and BTF and write them all as well from libctf. So I'm not competing here. It's more that I can possibly pick up the CTF the compiler's generating and spit something out which is suitable for BTF if it fits within the range limits and so on and so forth. So I'm hoping I'm just strictly adding to the utility of the system here rather than trying to compete with people. So why not just ignore all this completely and just use BTF? CTF has a wider scope. I don't think BTF is ever planned to be useful for user space, but I've got all sorts of ideas for CTF being used for C programs to introspect their own types, even if they're not in the kernel. It's got much wider range limits. I'm wondering, looking at the BTF range limits, which are the same as the Solaris ones, if no one's ever tried BTF converting all the types in a full enterprise kernel, including all the modules, because I tried it with CTF, with Solaris CTF, and there just isn't room. You run out. Even if you deduplicate things, there's more than 65,000 types in there. So at some point, BTF will need to expand its ranges. CTF already has, so I can probably give advice on how to do that. We will be able to omit BTF. I'm hoping we'll be able to translate in both directions. So you could pick it I haven't designed the API for this yet, but the idea is that we can sort of act as a universal translator in all directions for all of these types, with CTF always being able to handle a superset of all of them. This isn't really implemented yet, but it's a future goal. GCC has recently gained BPF support, the next talk, and with CTF support as well, we'll be able to generate CTF for BPF programs and hopefully convert it into BTF using the machinery I just mentioned. So again, this is still all being written, or at least the conversion part. So, what am I planning to do with all of this? Well, for a start, it would be nice to be able to use CTF in the kernel. But in order to do that, we'd need a version of libctf that would work in the kernel, or we might need one. And at the moment, it's purely user space. If it's going to be used in the kernel, it seems likely it would often be useful in atomic context. Panics, things like anything running in interrupt context, anything running from a trap. So we'd like a version of libctf which did no memory allocation at all. Or, well, not of libctf as a whole, but of the read side. I don't think we're ever going to want to create CTF dictionaries from inside the kernel, and libctf can do both. Creating a dictionary is much more complicated than reading one that's already present. One other caveat I should have put on the slide on the Solaris front, if anyone's ever tried creating dictionaries from Solaris libctf, it's terrifyingly slow. It gets exponentially slower the more you add to it. I fixed that a few months ago. It's not true of libctf. You can create containers and there's dictionaries and you can't see it in the profiles. I want to be able to support big enum values. BTF and CTF currently say its values, enumerated values must fit within 2 to the 32. C doesn't say that, and you can have any integral type, so it could easily have a 2 to the 64 minus 1 value, and the kernel has some. So I'm going to have to do a bit of a format change for that. libctf will of course keep its backward compatibility promise, so we'll be able to read the old ones.
I think on that specific point, C and C++ differ.
C certainly says any integral, and the kernel relies on it, so CTF had better handle it.
I remember because we ran into it. Some compilers in the claim, and you're right. They're different.
But you can certainly say 2 to the 32 plus 5 ULL in GCC and a CE num initializer, and it will work fine. So it would be nice if I could represent that rather than just saying, oh, I'm going to ignore that enumerated type, the enumerated value. No one's going to use it, right? We're going to, I'm considering adding a section for kernel function symbols, much like the one for kernel data symbols, so that you can go from a name to a full prototype, instead of just from an ELF symbol to a full prototype. But again, I only just thought of it, so that hasn't been designed at all. I'd like to support all of GNU-C, or at least more of GNU-C. The kernel uses vector extensions, which is something I only discovered recently, and there's no support for that in CTF yet. I can't remember where, it's somewhere in the RAID code. It uses vector types at the global and the static file scope. I want to be able to translate in all directions. I want a backtrace. We want a backtrace section, but which is not really designed. So I'm planning to, we'd like to take from everything, dwarf and orc. I think orc has the opposite of I'd like it to be simpler than dwarf. No interpreters, thank you. I hope we can describe most things without needing the complexity of exploits. I'd like to be able to be oriented to online debugging, and I think I say in a couple of pages later, yes, that we would like to be able to, we almost have the opposite view of orc. Orc, as I understand it, is interested in reducing complexity, even if it means increasing size, to reduce the complexity of the reader.
It's speed. It needs to be fast.
Well, I'm interested in that as well. But because I'm very much, I don't mind if the code is more complicated, as long as the format isn't complicated.
There is this Finnish character that has very specific views on complexity in the unwinder.
Well, I'm interested in reducing size here as well. Presumably the kernel's interested in reducing size because it's all in unswappable memory.
It's not been a problem. Orc has been designed for speed and for simplicity. Because when you unwind, specifically in bug and panics, everything's gone to shit.
Yes, I certainly don't want the unwinder to require memory allocation, for example. That would be a disaster area in most cases.
So orc has worked really well for us.
But I don't mind a tangle of conditionals, for example. But I would like to be able to take ideas from everybody on that because it hasn't really been designed. We've been working on everything else instead. On the format side, I'd like to increase compactness. Boosting all the ranges did reduce the compactness of the format a bit. I know how to get all of that back and more. For example, having a variant which only supports really for specific types, which only supports small type IDs, which is okay because that means you've put heavily referenced types at low IDs, and then it means you can use a smaller representation for any type that references them.
That's effectively the same concept as like JavaScript minify, right?
Well, except it would be done by the linkers.
Sure.
Pay attention. Yeah, we've already got overlapping representations, but the overlapping representations are for normal types and unbelievably gigantic types, and we should probably add ones for small types as well. I'd like to be able to put, I've tried optimizing the string table, which is gigantic. It's often the biggest part of CTF, and it's really hard to, CTF dictionaries, and it's quite hard to compress. I tried to compress it by splitting up at underscores and case changes and turning identifiers into links to lots of, and it was a great idea until you compressed it, and then the compression dictionary was destroyed by all its variation, and the size went up. But what I can do without adding any complex extra links anywhere is to say that this if the structure has a constant prefix on all its members, that we store that prefix once. And because there's no need to store a pointer to it, because if there's a prefix there, we just use it. It seems to me that would be turning symbols into zero, into nothing, and would be almost certain to reduce size, at least for things that have the standard of the old standard of constant prefix on every member of a structure. It's fairly common. You see it.
Yeah.
Yeah, like C does it. Yes, the historical reason is ridiculous, but certainly some people like it to make identifiers greppable. I like to try to burrows Wheeler compress as much as possible first to see if it's handleable in a sensible fashion. I'd like to try compressing with LZMA instead of just gzip. It seems like those are cheap ways to get piles of extra compactness with almost no effort. It wouldn't improve memory usage, but it would at least make the compressed format smaller. I want to get rid of our archives. It was an ad hoc format. It's okay for gigantic use cases like the kernel, but for almost every other use case, it'd be much more simple to just teach CTF what a translation unit is, so that you could have one dictionary with multiple types from different translation units in, which would mean they would magically share their string tables and so on and so forth, which would improve compactness more.
So the parent-child relation of archives seemed to make sense for modules.
Oh yes, yeah, that's what we're currently doing. We have a container, a dictionary with everything which is used by more than one module, and one dictionary per module. In fact, we shuffle things differently for the kernel than for everything else. For the kernel, things go in the per module dictionary if they're only used by one module. For almost everything else, we're saying that all types, unless they're conflicting, go in the global dictionary, and only conflicting ones go in per translation unit dictionaries, simply because it's smaller, and it's more likely the case that people will need most of the types. For the kernel, often you only need the types in the core kernel and a couple of modules, and there's no point even loading the rest. But this is all customizable. It's all implemented in this shared libctf linking machinery, so you can write your own link-like thing and use whatever strategy you see fit and deduplicate across that. Interestingly, when you're deduplicating, squashing things into one module per child has an interesting consequence. What happens if two translation units in a single module define types in conflicting fashions? What happens if you have two translation units that define the same structure in different ways, and a bunch of other translation units that just have opaque forwards to them? That's a case the kernel does actually use, and I know how to solve it in the deduplicator, but I haven't actually implemented it yet. We would chase, if there's only one, and if it's a non-conflicting use, we would link them all up so all the forwards would turn into links to the real structure. If there are two conflicting definitions, one of them would be considered canonical and would be lookable up when you looked at that structure by name. The other one would be hidden and would only be visible if you followed pointers specifically to that structure. And we pick it so that the one that had most pointers to it got made visible. I can't see another way to solve this problem. It's very rare. And all the forwards in that case would just stay forwards because we don't know which one they're referring to.
It might actually make sense to issue a warning.
Oh yeah, I might do that, but
fix
the problem is actually valid C. So,
well, I mean it is, but I mean
it's gruesome. It's gruesome, but it's valid C. So I want to be able to encode it without falling over.
But at least issue a warning so we can fix it. I mean, it is a pretty shit situation.
I might make it a warning that you can turn off and on, so that it could be turned on with the debugging options or something. Because I don't like it when normal kernel builds spray warnings that no users care about. But yes, I agree that it would be nice to. We should probably warn about this.
I mean, the rename is simple enough.
Yeah. Well, and if you've got other things that have forwards to it, which might be passed to either of them. It might require a major re-architecture. I don't claim to.
Don't we have Cochinelle for things like this?
I have seen uses mostly in the old ISA sound code. Who cares about the ISA sound code? Maybe.
I'm happily unfamiliar with that code.
And the last bit, I noticed the text size on this slide is still different, despite my attempt to try to fix it. I was wondering what I could do, which the kernel would find useful. In kernel-associated stuff, Dwarves has code to read the old Solaris and FreeBSD CTF already. I would be quite happy to, once I've got libctf reading everything, to submit a patch that has it using libctf instead, so it could read everything, and there wouldn't be quite so much code to maintain. I've been thinking about acting as a source of data for the kernel backtracers, but this is a bit tricky because either we need the in-kernel variant of libctf and all the CTF linked into the kernel and loaded, which uses more memory and people might say no to, or we'd need a user space helper that used libctf and you call down to it, which would obviously you couldn't do in the case of panics because there's no time, everything's dead.
We do very frequent backtraces from NMI context.
Oh, in that case, that pretty much destroys one of those options then in kernel then.
We do many backtraces from logdep.
Mm.
In
kernel,
backtraces
no malloc,
are important.
In kernel, no malloc. Well, we would certainly... We would certainly be able to improve, even without the backtrace section, we would certainly be able to improve the quality of backtraces because with the backtrace section, we could probably turn it from just function names into names and all the arguments and types, and you could add something that would let it drill down through them as well, which is something that I don't think people had considered before now because it seemed completely ridiculous, but it would suddenly become easy.
There is actually people working on some of that. Most specific for the function tracer. We already have the Ventry hook, and if you use the function graph tracer, we also do unspeakable things to the return.
That's a function tracer for you.
Yeah, I know. People were looking at having that print the function arguments and all that, and we've talked about doing it on backtraces as well, but nobody ever. Well, so if we have the information, we could maybe do it. It's not something I've personally have had a need for.
The option is there now, and it probably wouldn't be terribly difficult.
As long as you have the type info for functions, you can do it.
Basically, we've already got that. All I want to add is the parameter names.
Oh yeah, so strictly speaking, all we need for a specific function is how many arguments it has.
Oh,
and maybe a size.
Yeah. It depends on the argument. I mean, I'm sure there are some functions that get past chars and things.
And do you do not need to know what is the kind of each argument, so you can find it, according to the API? Like, okay.
So, I mean, if you know how many arguments it has, we already know what registers to look at because we have a purely register-based calling convention, at least on x86, 64. I mean, we do split the stack, but
where they are on the stack.
I just, yeah, but we have a kernel function for that. We just give it the number of arguments, and then it goes find it.
Depending on where you are in the function, that argument might have been overridden, right? So first you maybe say to the stack.
This is all the usual.
But for Ventry, it's still there.
For Ventry, yeah. Okay, I thought it was
It gets difficult.
Yes,
yeah.
I was thinking of full backtraces here, really, where you clearly need more than just look at the current function, current frame.
Well, actually, part of our motivation to work on this was that there are some people. This is in user land, but this who are interested in basically in a fast way to recover the original values passed to a given function whenever possible.
Without needing all the dwarf debug info because
exactly, without having to implement a little stack machine, so you can,
I prefer 2% or less of the size of the executable to 10 gig sort of thing. Microphone?
So one of the things that we're interested in is we would like to be able to do postmortem debugging without needing dwarf.
Well, you could certainly do that with what you've got.
Exactly. So
now.
for backtraces and being able to get arguments, that would be key for us.
Yes, we obviously can't do info locals because we're not tracking that sort of thing. But I think the goal of the backtrace section and all of this is to let BT work, which honestly, as far as I can tell, is 90% of what people do with GDB anyway. Most of the rest is runtime, and if you're messing about with breakpoints, then you've presumably got all the debug info.
Is there any way to get any of the argument attributes in there, or function attributes as well, like no return or non-null? Because if you can get non-null there, you can start.
Thank you. I hadn't thought of any of that, and that's a good thing to go in the next format revision.
Okay. If you can get that in there, you can make a backtrace that says this argument is null and it's not supposed to be.
Yeah, we should definitely be adding as many arguments as possible, attributes as possible. In most cases, I think it would basically be a bit flag of some kind. We've got the advantage that most functions don't have and most arguments don't have attributes, so it's not going to make things much larger, and most of them are single bit flags anyway. I was wondering if we could use it to help the, and other people were wondering if we could use it to help the KABI checker in some way. I mean, my biggest problem here is that I tried to understand what the KABI checker is doing, and it just drove me mad. Clearly adding, in most cases, adding things doesn't break the ABI, except that I think it would change structure sizes and would break the ABI. So if I understood what it was doing, maybe I could,
So on a personal note, I'd like to abolish KABI and not make anything there easier. I prefer to make it harder.
Oh yeah,
to preserve KABI.
Those of us who have to deal with enterprise kernels have to deal with this monster, and we'll have to deal with it no matter
Well,
what.
they're doing it wrong. And when I was in a position, I kept telling people that.
Oh yeah.
It's wrong on all levels.
Oh yeah, but I'm just trying to live in the world as it is, in which people want the KABI checker, and I'd like not to have to slow the build down by masses to building all the dwarf and then scanning it. It should be something that can be done like that with this tiny CTF thing, if possible.
Without KABI, some of us might not have paychecks.
Because we do have all the variables.
When I was in Red Hat in the RHEL team, what I suggested is for all the magic modules that we apparently support, get us the source code, stick it in the RHEL tree, and we'll just update it right along with all the other things.
The problem there is that
you
what
could
happens
have
every time the ABI changes incompatibly, which it does every few releases, you have to go screaming back to the people who would given you the patches, and I don't know how long you'd have to wait for them to come up with fixes.
But, I mean, if it's all in the RHEL tree, all the magic modules, the NVIDIA crap, the file system monkeys from wherever, there is no KABI. You just build new versions of it. Life would be so much easier.
I know, I know, but as long as we have a KABI checker, I'd like to make it faster to use, and not so horrifying. Because I mean, one advantage of this is not just a format; it's a library. So you can just walk around these things with a couple of function calls. And I'll certainly, if we do get a kernel version, I'll keep the same API. And ideally, of course, anyone with binutils would have access to this library once this all lands and is released. The next released binutils will have the library, but not the linker side, because that's still being reviewed. I've got some more a link to an LWN article in which I completely monopolized the comment thread with more API ideas and so on. Anyone who hasn't already read it, and probably everyone in this room reads LWN anyway, there's more stuff there. And I think we're now at questions. I wish I knew how to stop it doing this. Let's go back to the end. Does anyone have any more things I could use this for? Any more improvements?
Well, so I'm going to want to use this because I've been looking for something like this for a long time.
Yes. Users, excellent.
So I'm going to want to use this to generate Python bindings so that we don't have to write Python bindings in C ever again, right? So write a pure Python, write a Python module that then loads these and generates bindings dynamically as you try to use something, and then write Python bindings to make things Pythonic in pure Python. So you never have mallet-free problems at all because these are just Python objects. So that's really going to help. So I don't have a question. I'm just saying I think we'll probably find some things that you're not expecting.
I mean, one of the first questions I got when this hit binutils is, will we support C++? And I have no theoretic, there is no format-related reason why we can't have a CTF variant which looks the same to all users, with extra API, obviously, which supports C++. It's just it would make my mind melt to design this. Some of the revisions to allow it to do sort of large-scale reading and writing of different formats will also help with completely different languages like this. I've had people say, where's the spec? I wrote it on Friday. Where's the spec? I want to write a Rust version of this, that sort of thing. It's, the more the merrier as far as I'm concerned. The advantage, this is one of the reasons why I've got this format, read, write, all the old versions thing, is simply that this means that other users, including other format interpreters, aren't required to keep up with everything I'm doing. They can just feed it to me and say, hand back the latest version, or vice versa. I haven't yet figured out what happens if someone takes some CTF with 10 million types in it and says, give me BTF. Or if someone takes some CTF with an enum bit field and says, give me BTF. I think in the enum bit field case, we just drop that one type, but if there were just too many types, we'd have to say we can't convert this.
Issue a warning.
Well, it would be an error code from the, it's not a, these are all library APIs, so you get an error code back. It's just, this is just too big. a possible future enhancement might be ways to split these things up in that case, but I'm not going to write it. Because splitting type containers up is very hard because all the types can link to each other. You can easily end up with 10 times as many types, and you still haven't shrunk the size of each by any great degree. Oh, and speed-wise, by the way, I thought people might want to know how fast deduplicators can be. The old dwarf to CTF deduplicator I wrote, it started out taking about 1.5 minutes. After the recent speed-ups to libctf, it now takes about 40 seconds, and most of that is the overhead of reading all that dwarf in. So I would hope, I've got a kernel, I've tried CTF generation with a non-deduplicating linker, and it spits out 55 million type, horrifying CTF file, which is about 70 meg in size. The fact that it only takes a few minutes just to do something on that scale suggests that there's no fundamental speed problems in the library anymore. I don't know how fast the deduplicator is, but as of last month, LD and GDB and all the rest of the stuff in binutils could, in theory, use threads. So I'm probably going to make it multi-threaded if need be to pull in CTF from multiple translation units at the same time or something like that in the future.
And actually related to that, in GNU we very recently introduced a pthreads module in GNU-lib, written by Bruno Heibel, who is a monster. And, and we are starting in GNU in general, because this basically is giving us the ability to parallelize our programs in a way that, in a portable way. And as everything that Bruno does, it's extremely portable. So that means Windows, MinGB, whatever. And probably Gold and even LD maybe, but there is BFT there to deal with. But we are going to start to parallelize more.
Suffice to say that I noted when I started working for a database company that I stopped working on databases. When I started contributing to GNU, I started having to use Windows because I was having to compile stuff on MinGW to make sure it worked there. So Bruno is a monster of portability. So if people have more ideas, they are just the binutils list is where all this stuff is getting done. So if people have more ideas, do please come into the binutils list and offer suggestions. I will be generally happy to implement any of them. I hope this is of general use. Hell, in the future, in the distant future, I hope Clang learns to do this as well. It's just there are licensing problems, so I'm not even thinking about it at the moment.
What licensing problems are there?
At the moment, well, the license history of libctf is interesting. It started out weird proprietary. It turned to CDDL. From that, it turned into UPL. Into a union of UPL and GPL v2, because we're using it at the kernel side as well in the build tools. Once it moved into binutils, it became GPL v3+, along with everything else in binutils. But I'm almost certain that we could turn it probably into LGPL v2+, so the kernel could use it, and so on and so forth. I'm fully sure that turning it into BSD license so we can use it in Clang will cause something that would cause people to scream. I don't know. I'm not saying one way or the other, and I'm not going near this because people will bite my head off almost no matter what I say. In fact, I have the gestures. So I do not know. All I know is the license has changed in the past. It may change in the future. I would like everyone to be able to use it, but copyright law tries to stop that from happening. I don't like code duplication, but at least we now have a spec. So if people do need to duplicate it, they can. I will add to the spec in future to provide differences between the current CTF and all the older versions, so that you can easily tell, sort of what on earth is the difference between CTF v2 and CTF v3. A CTF v4 will be coming, and then I'll change the v3 to say what's different from that. And I'm probably also going to add something that says what's different between BTF and CTF v whatever, just so they're all documented in one place. I'm sick of researching this in dozens of source trees. But that's all going to come in the next few weeks, probably. Finishing the documentation is very important. And the linker. Anyway, that's it, I think. My God, I blew my time by miles. I'm sorry.
No, because this is important stuff.
And also
not like what follows that.
Sorry, I need to switch screens back without having to reboot the machine like last time.
I'm going to need the cable, the VGA to the HDMI converter.
And
I have my screen. I didn't explode.
This works? No? Oh, here we go. No, press the mute button. Is it working?
Press the mute button.
Well, he says that it is.
Press the mute button.
Now? Oh, shit. Oh. Down, down. Okay, we have 20 minutes, so this is going to be fast. So this is about the eBPF support in the GNU toolchain. Basically, you can use, GCC, binutils, and whatnot to generate your BPF programs. So first, I am not a tracing person. All right? I think that I should mention this because I am just the compiler guy. Basically, you give me some C source code, and then I give you some, hopefully, very well compiled, BPF program. So BPF tracing, this, that, I actually don't care about it that much. I mean, I care about it because it's the main, maybe the main consumers of this, but I actually don't know that much about it. So the project itself that we started a few months ago, basically the first phase, which is done, it was to add a BPF support to the toolchain itself. So we introduced a new GNU triplet, which is this BPF unknown none, in BFD, the ELF headers in binutils and whatnot. Then we made a first port of binutils, meaning supporting the assembler, opcodes, disassembler, and this was upstream already in May 2019. Of course, back in those first versions, they contained a lot of errors, so we had to do some amendments there. We are not done yet with that. And then yesterday, the GCC support got accepted upstream, and I did a commit yesterday, just in time. But, so the first phase is done. The second phase is to make the BPF programs that GCC compiles suitable to be basically loaded and executed by the kernel. Because one thing is to generate BPF programs in an L file, something completely different is for those programs to be palatable, to the kernel itself. We shall see now that there are two aspects of this. First, you have a sort of IBI, a sort of application binary interface, which is actually enforced by the kernel loaders, which are the kernel components that basically get the L file that you provide with a program and loads it into the kernel, translating them into some syscalls or whatever. And then there is the kernel verifier, which basically determines what a BPF program can be running in the kernel in a safe way or not. If it is not, then it will not run it. That phase is starting now, and it is obviously a continuous activity. All right, because the kernel verifier changes, it becomes more sophisticated with time, which basically translates into lifting some of the restrictions in BPF programs. And then, of course, we need to keep the compiler up to date to that. Then the phase number 3, which actually is in parallel with the phase number 2, is to also add additional components for the BPF developers. Because having an assembler and a compiler, obviously, it is very useful. But especially in targets like this, which is not that much different to an embedded target, for example, the developers for that platform, they will benefit very much,
from things like a simulator. I will talk more about the simulator we are working on, which includes, emulating some of the kernel contexts, that the BPF programs see. So, the port itself. Okay, BPF is very peculiar, all right? Especially for someone like me who comes, from working on the Spark backend, for example, of the compiler. BPF is something completely different. At first sight, it looks like a pretty much harmless, little cute, architecture, with, I don't know, 11 64-bit registers, very uniform encoding for instructions, arithmetic instructions, logical branches. It looks pretty harmless and nice, but trust me, it's not. Because there are some characteristics of the instruction sets, there are some omissions there which come from, I don't know, probably security concerns or the way the instruction set has been designed and, and evolved. That makes compiling BPF challenging. Other than that, I'm not going to get into detail here. I'm going to do a big talk in the Cauldron later in this week, and I have a lot of slides for that about the fun, and the fun and the interesting, how compiling BPF can make your life much more interesting and fun. But so if you are curious about it, I forward you to the slides that will be published or the video or whatever. Anyway, other than that, some of the characteristics are that first, kernel helpers, I decided to implement them as compiler built-ins. This is slightly different to what LLVM does. LLVM provides you with a header file, the bpfhelpers.h, and basically it relies on some specific behavior of LLVM when you build with -02 in a way that at the end, you get the instruction that you need to call a kernel helper. Okay, I think that is very fragile, so I preferred to add, explicit compiler built-ins that will generate always, it doesn't matter what optimization level you use, it will generate the right instruction for you. This is much more robust, in my opinion. Of course, it comes as the cost, that you have to maintain an explicit list of helpers. But then again, if you look at this option here, we also took the pains of adding to the compiler a -m kernel option, which is similar to the -m CPU option that you find in more conventional targets. And basically, you can specify the version of the kernel where you intend to run your BPF program. And then, for example, GCC will tell you if you are trying to use a helper function that it does not exist in that kernel version.
So this mkernel version thing, will that then also grow to include all the enterprise kernel versions that have random backports and God knows what?
I have no idea. Maybe, yeah.
Awesome.
Is that necessary?
Yeah, how this works actually. In RHEL, we have quite a lot of backported stuff to...
How it actually work? Because in enterprises kernel, distribution kernels, we have a lot of things backported from newer kernel versions. So you have 4.18 with the BPF at 5.0 level.
Uh-huh.
So how does this work?
Well, for this first implementation, I'm using mainline release numbers. Now, you are telling me that in RHEL, for example, you have backports, so this is not enough. So then we should come with a solution for that.
Yeah, it's basically the old problem, not relying on versions, but on features present.
We could support both. I mean, or if relying on features makes this obsolete or not that useful, we can remove this, no problem. What would you do? Would you group the helpers, for example, in functionality, or? I mean, there is another option.
I don't know.
If you always use kernel latest, it will get any helper.
Honestly, I think that hard coding BPL helpers into GCC is not a good solution.
Because of backporting issues, it's not really practical.
Okay, so you think that supporting this option is not
practical.
It's not practical.
Because 4.0, people could use the latest features. So sometimes you have a later version, you may do not have old helpers. So all these could mix up.
My suggestion would be that is to move that header into the UAPI headers in the kernel, and pick it up from there, and specify the, you know, and that way, if you need additional information about what's available in the kernel, you can also, we could also add pragmas to that header file, or whatever, you know, whatever you would prefer.
But this is orthogonal to the header file. I mean, this is about, because I know that in the LLVM port, it is the BPF helpers header file that basically determine which kernel helpers are available or not. But in GCC, it is the existing compiler built-ins which are available or not.
But what I'm saying is you can, you know, you could get that information, you know, instead of mkernel, you could do that from a pragma in a header file.
Okay, yeah.
And that way that pragma can be adjusted to match whatever distro kernel does. It would be not really the version of the kernel, it would be the version of BPF that kernel supports.
Well, that I always try to, I mean, it's not always possible to do it, but as from the perspective of the compiler, I always try to abstract the fact that the BPF program is going to be run in a kernel, for example.
Right, but
so yeah.
But whatever options, you know, we can encode that information in a kernel header file and give it to you in whatever format you want, which I'm assuming is, you know, pragmas. And that is a much better solution than putting it on the command line.
Okay.
There's already one here. Another alternative, given that the set of it seems like the set of backports could be variable on a per distro basis, and you can't turn that into a linear BPF version, ascending BPF version number, is to say that all of these versions correspond to a file which is a mapping somewhere under userlib gcc BPF or something, and the distro kernels could simply ship one of these files, and then all of a sudden 4.0-rel would work, and it would pick up the appropriate mappings from there. And then you don't need to ship anything. And this also means that new kernels could be easily supported by shipping one extra file without needing to ship a whole new GCC.
Okay. Well, we should discuss about it. Yes.
It is basically what I said.
Yeah.
I believe it should be in the kernel API header directory.
Which basically brings me to the next point, which is the BPF helpers header file. Now, at the moment, currently the kernel is providing a BPF underscore helpers.h file, which is in the kernel tree, which for several reasons is LLVM specific, which makes full sense, because up to now, you know, I mean, LLVM was sort of a requirement to do this. Yes?
I disagree with that. And
with what?
I mean, LLVM specific. Basically, the existing code has to be compiled with GCC as well. So you cannot force users to abandon the
BPF underscore helpers is LLVM specific.
You can have another one, but I think a kernel community will not like it.
No, well, what I think it should happen is to change it so it also works with GCC. I mean, the first thing that it has that is LLVM specific is that it includes architecture dependent kernel headers. And that will not work with GCC.
Another thing I think, and you should just completely get rid of this kernel thing at all, and whatever compiler generates the code, it should generally run all kernels, and it shouldn't really compare. And whether a particular helper available or not, that's application developer's job. It's not really compiler's job. And there may be some options, and we can have like a CPU generation version 1, version 2, or some architecture and features. It could be added, but we shouldn't really care about the kernel version at all.
I disagree with that.
Yeah.
I mean, because I try to apply exactly the same concepts and approaches that we use in other architectures.
Another thing about your compiler buildings, I think is also a bad idea. The reason is that basically means your compiler, the GCC, is tied to a kernel version. That's a bad. that means new kernel versions, old GCC won't work.
How is that different to the compiler being tied to some specific vector extensions or instructions existing in an architecture?
Yeah, because some people just have old GCC.
Yeah, but what is the difference? Can you please explain to me the difference?
The difference is the GCC, if you have these built-ins and it is an old built-in, and then suddenly you get a new kernel, and it won't be able to issue helpers for the new one, because the new kernel version has new helpers, right?
Well, actually, you can.
Unless
I mean, you can generate a call constant, which is what you do with in BPF underscore helpers.
No, I mean helpers, new helpers. For example, you have a packet processing or chasing something. You said, okay, I know I have a BPF chase SKB for some networking stuff. Only available in new kernel, not older kernel. And
Yes.
then you tie to a new kernel for BCC or this helper support. Then you cannot compile for the new kernel.
We can add mechanisms to do that. The compiler built-ins, I like the approach because, for example, it does, I don't know, like arguments checking, for example. So if you pass the wrong arguments to a compiler helper, it actually tells you at compile time. You don't have to wait for the kernel to
we
complain.
can discuss offline about the best way to do that, but to fix the built-ins in a compiler implementation at a particular version is basically won't work.
Okay, I'm absolutely interested on your opinions on that. And actually, you know, I think that it's about time that we have this kind of discussions online. Yeah. Well, the BPF helpers, dash helpers, not underscore helpers.h, that at the moment GCC is distributing, I want to get rid of it because I think that we can all use the same header in the kernel tree. Or, you know, I mean, it makes full sense. But for the moment, GCC has this BPF dash helpers instead of underscore helper. Probably we will be able to work out, you know, some common grounds here. Well, also, you have an option to specify in the endianness, exactly like the LLVM does. And also, I had to introduce a new option here, which is to increase the limit on the frame size, which is limited by BPF. More about this later. Oh, well. Okay, one of the things I did was to try to support as much C as possible. But the BPF platform architecture is so restrictive that that's not always possible. I try to do, for example, this is something that I would like to discuss with you as well. You know, I mean, how can we come, you know, with some general common mechanisms to do, you know, to support a loca, for example, things like that. So, does it work? Yes. Those tests are all compiling tests. They are not run tests, all right? That will have to wait for the simulator. But yeah, it sorts, you know, I think that the backend and the GCC maintainers, global maintainers agrees with that. It looks like it's in a good shape. So, first question I have for you. How should I call this thing? Because, you know, I mean, CBPF, okay, eBPF, and now what should I do? Should I call it eBPF or should I change everything to BPF?
Typically, we suggest the BPF.
BPF, okay, fine. So I think I did the right thing, maybe instinctively since the beginning, because I'm using BPF in symbols, triple the CTC, and you know, and eBPF in document. Okay, I will change it in GCC.
I think you should call it CTF. Let's make it even more shiny.
No. Okay, then I want to propose. I mean, this is something I'm actually currently working on it. The name is not important. I don't care about the name. I need a less restrictive version of BPF so I can test my compiler properly. And I thought about calling it, you know, XBPF or experimental BPF, but again, the name is not important, right? I am open to any name. Basically, the fact is this is a virtual architecture, right? So I need to be able, you know, to change the stack frame size so I can compile C functions, you know, like, for example, a lot of local variables. I need an indirect call instruction. I noticed that in LLVM you are actually generating one, and I will use the same encoding that you are using, because why not? Also, In a BPF program, when a function calls another, it is possible for the Kali to access the stack frame of the caller, but only using absolute addressing. I mean, you cannot use the frame pointer of the Kali to access, you know, the stack frame of the caller. In this XBPF, I plan to actually allow to access the caller stack frame using the frame pointer in the Kali. Why? So I can support passing arguments on the stack, so I can get rid of the limit of 5 words, you know, passing as arguments to the functions. And also that will give me also the possibility of do stack traces, right? Like a back tracker, which could be, I think, very useful for debugging your BPF program. Also, I want to assign division instruction. I want it. I mean, also, you know, to avoid, because at the moment, GCC generates a fun call if it sees that. So, basically, the idea is that you compile your BPF program as an XBPF program, and then you can go, you know, go forward avoid those restrictions. What is the purpose of it? First, so I can test my compiler properly. Because at the moment, I have to disable hundreds and hundreds and hundreds of tests in GCC because they use more than 5 arguments in functions, because they have the stack limitation, which is limited to 512 bytes by default, and so on. And that is bad for my testing, because I understand that you cannot run those programs in the kernel, but I need to test my compiler. So we are basically negating the possibility to ourselves to, you know, to use our test suite only because of those limitations. Also, I said already, to debug your BPF program, so you can use, while debugging it in a debugger, back traces. Also, I think it will be interesting to have, you know, as a sandbox, you know, so you could experiment, you know, with lifting, you know, some of the restrictions in the future, maybe along with working the kernel verifier. And also, and I am very interested on this last point, to explore a bit more, to leverage ELF more, right? Because, for example, in the GNU toolchain now, LD knows about BPF. It sort of links, but the BPF programs are very, very strange in the sense that they don't really correspond to the ELF concepts like executable with a single entry point, initializers, finalizers, because it uses a completely different model where you have several entry points and so on. I think that having this XBPF thing, it could also allow us to play a bit, you know, and explore possibilities of leveraging ELF a bit more than it's used right now. And then it will be awesome, you know, if in LLVM you want to implement the same thing or something similar, so we can get, we can agree, you know, something like this. So you can probably, I'm sure it will be useful for you also for running the LLVM test suite. Also, in my opinion, one of the reasons why of using a compiler is that you want the compiler, I mean, you want the errors, you know, to as soon as possible in the development process, right? And generally speaking, you don't want to have to wait until you do a syscall in the kernel, you know, to get the verifier rejecting your problem. I know that the verifier is extremely sophisticated, and it is getting more and more sophisticated. But I really want the compiler and also the simulator to do a similar job that the verifier is doing. But I definitely don't want to replicate, you know, the logic of the kernel verifier there. So my question for you is there a way to somehow, you know, access or use or reuse the kernel verifier from userland, from user space? Maybe a program, maybe a library, I don't know.
Currently, there's some BPF fuzzy work actually take the verifier to the user space, but it's really a pain to maintain that.
Yeah.
And whenever the verifier changes and fuzzier some kinds of interface changes, they need to add or remove some kind of like, because they need to simulate all these K-malloc, K-free, IDR stuff, some other stuff. So it's really, so typically people do once a while, like every 3 or 6 months. They do one a while, some people, and they run it and make changes, test the verifier. We don't do it very often.
But is this something you would like to have in LLVM as well?
I think that is not scalable, this approach. So take a verifier, changes so often, and it's not a scalable approach.
And can you think on some other alternative approach that will allow us to do this?
Yeah, I don't have.
Okay, we can think about it. Yeah.
I just thought of something gruesome. Sorry.
Yeah, it's not the same problem the device 3 are having. It's leave FTD.
I have no idea about that.
It's exactly the same. There's something called leave FTD, which is how to handle a device 3, and it's inside the kernel, and it's also a library. So, no, I think I'm not completely sure, but it's the same. So it's also used by the kernel tree. So maybe you can take a look of what they are doing and do the same.
FDT.
File device 3.
Yes, FDT.
I will. Thanks for the suggestion.
I just had a completely gruesome idea, which is leverage user mode Linux. If you could add some way to call into the verifier directory, which is only available to UML, you could compile UML and invoke the verifier.
Before doing that, I will just do the syscall and check for the error message. Yeah. The problem with that, it doesn't tell me what happened. It just tells me that the program is not valid. Okay, the ABI. Okay, so the kernel verifier is about if a program is secure enough or safe enough to be executed in the kernel context. But then on the other side, in compiled BPF, basically is what constitutes a valid ELF BPF program, right? At the moment, this is defined by what the LLVM backend produces, and what the kernel loaders, this BPF leaf. Is it BPF leaf or leaf BPF? I always get so confused about that. And BPF load.c, which is a sample that is around in the kernel sources. Okay, I mean, I'm not criticizing it because I think it's normal, right? Because that's the only implementation right now. But I really think, and I would really appreciate, if we could have some sort of common place where we could document that stuff in the future. So it will be nice, and we have to get in touch, I think. And then, related to that, well, now there is LLVM, now there is also GCC. The kernel is the consuming for now, but there could be also simulators and whatnot. And also, I think the trace has been changed to it has a compiler as well, because it compiles from a language, the D language. And I heard yesterday in the BPF trace session that they also want to start generating BPF, compiled BPF as well themselves. So I think we need to coordinate somehow for two reasons. One, because me particularly, as the maintainer of the BPF support in GCC and binutils, I need to be in the loop. I mean, because I can run after you, but that's not going to work very well. And also, we want to also to contribute to it, right? So, for example, I don't know, this new addition of the core, I don't know how you pronounce it. This compile once, run everywhere, which is very interesting, by the way. Okay, that involves adding new relocations, for example. So it would be nice if we could have a mailing list for whatever, where we could, hey, what about adding this relocation of this type, this number, and handle it this way, right? And then we can talk about it and maybe publish it somewhere. I don't care where that could be. It could be in the BPF mailing list or in the kernel, or I don't know. I don't care. But it will be very nice. And that was it. We are already 10 minutes late. Questions? No? Yes?
Apparently there is, so get one of those things. Oh, yeah, sorry. No.
Yeah, thank you. So how about BTF? Because you were talking about, debugging and so on and so forth.
Yes.
Yeah.
Well, BTF is more important for GCC than you may think because, again, GCC doesn't have an integrated assembler like the LLVM does. Even though the LLVM integrated assembler doesn't work for every case. I have to say that too. So, for us, it's a need. These compiled ones run everywhere. For us, it's a fundamental need. It's not only, that a nicety. So, of course, we need to generate BTF or something equivalent. Now, my understanding is that the idea is to generate BTF for the kernel and then generate header files from the BTF, right? As far as I understood. So yes, now one of the next steps in GCC, which is something I want to discuss in the Cauldron with the other GCC maintainers, is that how can we generate BTF? Because now we are in the process of adding CTF generation in the kernel. So in the kernel in GCC. So I don't know if we will generate CTF and then translate from CTF to BTF, and so we can use the kernel scripts, whatever it is, that will translate from BTF to header files, or generate BTF directly, which also has some complications because in the compiler, well, you know about that, they try to use DORF internally as the canonical debugging format and generate everything else from it. It has to be discussed. But of course, we need to generate BTF or CTF or something equivalent, for sure.
Yeah, so we need to generate it, and we also need to be able to read it and manipulate it. So this is a kind of a shout out to whoever is involved with that. Because, okay, it seems to me that, so BTF is getting into the kernel, right? So that's a fact, right? And so people need to read it. I guess when I say people, the kernel first, right? Needs to be able to read it and do stuff with it. Would it be reasonable to ask that the facilities to read it be designed, or I don't know, as a library, reusable something?
As noted, libctf will gain the ability to both read and write. Sorry. Oh, God.
The library or
as noted,
libbpf.
Yes. And as noted, although actually reading the BTF will require allocations, I see no reason why the no-malloc version of the CTF I was talking about wouldn't be able to feed you BTF from CTF on the fly, as long as you're not in atomic context when you open it. Why would you be in atomic context when you're opening BTF? So yes, I certainly hope we can help with that.
Yeah, well, what I mentioned is today the library called libbpf already available with the API try to read the BTF from basically to load the BTF and to the kernel and to read the BTF out of the kernel. Already API for that.
And can it be?
It's a C library.
Yeah, okay, so you can read, BTF from any ELF binary.
Yeah, you can read the BTF from a file and display that and load to kernel, or you can read the BTF from kernel.
And if you wanted to be able to pull it out of an arbitrary ELF section, I'm sure I can find a way to leverage libctf's ability to do that with CTF and connect it with the libbtf thing in some way, and we'll find some way to work together.
Thank you.
Okay, so we are super late, and I am also closing the Toolchain micro conference, and thank you everyone for coming. Thank you for the presenters, and because it was nice to have you and I hope it has been useful, and I hope we have, from the notes and everything, that we moved forward in several areas today. So thank you.